సో ఏమన్నా ప్రొసీజర్ ఉందా? ఏమన్నా ప్రొసీజర్ ఉంది ఇంట్రడక్షన్ చెప్పేది ముందల? Hello students, welcome to the IMS GATE Academy. I am Ravi Bogdula. Okay. Hello students, once you confirm me that my voice is audible, right, all of you? Just confirm me by the comment so that we can begin the sessions. So once again I am introducing myself. I am Ravi Bogdula. I am mentor at IMS GATE Academy. Today we are going to discuss the quick revision on computer organization architecture. Exactly we have a 10 days time from tomorrow. If you see, exactly 10 days time we have for the GATE examination, and this is a time where we have to revise the subject entirely. So many times revision is required. So today I am going to spend almost 3 to 4 hours time to do the revision on computer organization architecture from beginning to ending. So few problems also I consider. So we'll solve the problems, we'll see the various topics, the how we can understand, as well as we see with some we'll take some formulas. So how to remember the formulas, how to understand the formulas, that part also we'll observe. So let's begin the session. Just confirm me all of you, am I audible, right? Everyone. So I hope I am audible. So now from the subject COA is concerned, so what are the topics, what are the things we are going to be see in this session, we'll observe here. So let me write the various syllabus from the computer organization architecture, the things which I am going to discuss entire session. So initially we will focusing on introduction part, that is a number representation, number representation. So number representation followed by memory organization, will observe memory organization, memory organization followed by, we'll see the machine instructions, instruction format, the followed by addressing modes and instruction pipeline. The lastly we see the IO organization. So these are the major areas which we are going to be covered from the computer organization architecture. The first aspect, the number representation. Here we are not discussing any number systems or number conversions. I hope you done from the digital logic design. Here number representation we are talking majorly fixed point number representation, fixed point, comma floating point number representation, floating point. Our major focus goes the revision on fixed point, floating point. In the memory organization, so we'll observe the memory hierarchy, main memory, cache memories as well as secondary memory we see. So in the third chapter, there is instruction format and the classification of instructions, various addressing modes and instruction pipeline, like various stages, the basics of the instruction pipeline followed by the hazards, instruction pipeline hazards, their solutions also we can observe. The lastly, our focus goes IO organization. Here in the IO organization, the major focus goes to data transfer methods in which DMA controller, because the gate exam point of view we consider the areas from the IO organization we can expect the question from DMA part. Like if I talk about number system first, so we can get the compulsory, we can get the question from the floating point area, and when it is considered memory organization, in which the one question at least we can expect from the memory hierarchy on cache memories and main memories also. So we'll do the quick revision on each and every topic, ma. So I hope most of you already studied the subject COA, past your preparation. Now the prior to the exam, so we have a hardly 10 days we have, right, very 10 days near to the examination. So this moment, so revising the entire things is very important. So most of you prepare the quick notes for each and every subject. You might be prepared the quick notes, short notes, we call short notes. The short note kind of things we are going to revise. The short note contain the important statement, important formulas, the important topics you might be specified, right? Similar way I structurized from beginning, like the basics of the chapter to the end of the chapter. All the various important points are gathered. So let us revise all of them. I hope definitely this session going to be useful to you a lot. So let's begin the session, ma. Here, so first of all, we'll focus, like this subject is like subject COA, computer organization architecture. The computer organization architecture major focus goes on two aspects will be there. The first is the computer organization and second is computer architecture. There are two terms, right? Computer organization architecture. There are two terms are there, organization, architecture. Let's have a quick differentiation between the organization architecture, then we'll enter into number representation part, ma. So from computer organization, what this computer organization talking about? You can look at the word organization. Something it is going to be organized, right? Computer organization, nothing, organization. The word, if you see the organization, something is organization. So what is this organizations are? So computer organization special focus on the physical components of the computer system, or you can understand physical building blocks of the computer system. It is focusing on the physical building blocks of the computer system. So what are the physical building blocks? Like components you see, the CPU, central processing unit, memory components and IO devices. It is just focusing on the physical devices. So what is focus? The physical devices, their interconnection to improve the system performance. Look at here mentioned. It is more concerned with the physical components and their interconnection with the perspective of the improving the performance here. In other way I mentioned, it deals with the study of the behavior and structure of the different building blocks of the computer system. The building blocks, if I talk about, we have a processor, memory components and IO devices. How these all the components are organized, their interconnection in order to improve the system performance. So like if you see when you want to buy any mobile or any computer system, there are two concerns always will be there, right? What are two concerns? One is cost of the system, cost of the system, cost of the mobile. Second is the performance. So now computer organization is always concerned with to improve the system performance and to minimize the cost of the system here. If you observe from the last decade onwards, a lot of improvement happened in the computer system, right? So from Pentium 4 to Pentium 4, later dual core processor, core to dual processor came in picture. Now i3, i5, i7 if you see. So like in terms of CPU, clock rate also improved, like multi-programming, like multitasking, multi-processing, like multi-threading. There are many things came into picture, right? So we are trying to evolve the computer system, so but keeping the cost is minimal. You see, like the earlier almost 15 years ago, if you see, if you want a basic computer, if you want to purchase, so almost 25 to 30,000 need to be spent. You may get the i3, like Pentium 3 or Pentium 4 processor. Today, same amount 35,000 if you spend it, i3 processor system, you can get it, right? So performance is evolved a lot. The performance of the computer system evolved a lot. So that's what I understand. Computer organization always is concerned with what? Improving the system performance. Sir, how the system performance can be improved, sir? Please understand. The system performance can be improved organizing the various, various ways, like various things, you understand. Organizing the various things. So it is major focus, like, the areas you see. The areas where we can improvise under number representation. So that we number nothing but, let me take in terms of under data representation we can improvise it. Sir, how data representation can be improved, sir? Like, you understand the floating point number representation. If you see the conventional approach something and the modern approach is something, there we can improvise it. And second aspect is talking about store. How data is stored in a computer system, how you are going to access from the memory. So store and access and processing the data, nothing but execution of this data are in programs. So execution of programs, the final result of the program will be stored in a secondary memory devices, right? Memory, that secondary memory it will store. How these various like devices communicated each other, this communication. So these are the areas we can improvise it. These are the areas we can improvise. So these are the areas only, nothing but you understand is entire our syllabus. The first chapter is number representation. Second is what? Memory hierarchy, memory organization, store and access. How we are storing the data into memory components, how we are going to access it, the store and access. Third one is the processing, nothing but execution of the programs. You understand, execution of programs, nothing but is majorly focusing on the processor, like how instruction formats are there, how the instructions are going to be executed in a CPU, the ALU, like those things. And communication, nothing but how peripheral devices are communicating to the processor, how we provide this communication environment. You understand, like we have interfaces, IO interface, IO channel, IO module. It is providing the interface between the IO device to CPU so that they can communicate each other. So these are the areas need to be improvised. So that that's what is talking about computer organization. So we can improve the system performance. Now the conclusion is that computer organization is focusing improving the system performance. So by organizing this physical component of the computer system, the areas I mentioned. Fine. So I hope you understand the computer organization. Quickly we will understand of the computer architecture. See, the computer architecture is major concern with please understand conceptual view of the system. I mentioned it deals with the conceptual view of the system, and its concerns are instruction set architecture, ISA, and addressing modes and data format. So what are the three things, sir? Very simple, you have to understand. So in order to design the computer system, some architecture need to be designed. Architecture nothing but it is a concept. It is not focusing the relation with the hardware. Computer architecture is not focusing the how you are realizing the concepts by using the hardware. It is only focusing on that how concept is implemented. Concept means what is the instruction format, what are the classification of instruction, how many instructions supporting, how registers are formatted, how memory components are connected, like how connected, how fetching is happened. Simple thing I can say, how fetching will happen from the memory, instruction fetching, instruction decode, execution. So these all are focused by the computer architecture. Other way you understand simply, if you want to construct the house, we need a architecture, right? So logical design of your house, if you take the needing architecture. So you approach some architecture, you will give a design. So design nothing but design of your work. The logical design will there. So by looking this design, you will start implementing. By looking this design, start implementing the house, right? Similarly, you understand. So we are thinking, we have to look into the designing of this paperwork. So means how components are connected, how you are talking about instruction format, what are the various addressing modes are there, how they are going to help us, what is the data format, either we can store like EBCD or like EBCDIC or ASCII code, what format data is represented. So these all the things are focused by the computer architecture. So computer architecture is a conceptual thing, and implementation can be done by using hardware. This all the concepts, once you build it, then you can implement by using hardware. So during this implementation, that implementation part should happen in proper organization. So now COA is talking about that organization of this component so that system performance can be improved. So this is both concerns of the CO and CA. I hope you understand exact differentiation between computer architecture and computer organization. Yes, so please respond me that. So point is clear so that I can move to next topic. Next point we can understand. So first focus, we'll go and see the first chapter, that's number representation we can observe. The first part. So just before going to a few point I mentioned to exactly differentiation. The COA, it is focused on the internal view of the system. Its attributes are processor, memory, IO devices, as I mentioned. So different building blocks of the computer system, if you see, these are the things. And the CA is focused on conceptual or external view of the system by the machine level instruction, machine level instruction. It's like a machine level programmer point of view. So how machine level program is going to view the system. So that is concerned. Its attributes are like internal part of C, the registers and memory, instruction set architecture, instruction format, addressing mode and data format. So these are the major attributes of a computer architecture, and these are the major attributes of a computer organization. I hope you understand the differentiation between CO and CA. So next move on to the first area, number representation. Here number representation, like from digital logic point of view, so most of you already you studied, right, various number system, their conversions like binary to decimal, decimal to octal, octal to binary, like binary to hexadecimal. These are the conversions you already you studied from the digital logic design, right? Now I am not so concerned of this number systems and their conversions. Will focus on the representation part, the various number system representation. So major focus goes on floating point area, because floating point area we can expect one question, one or two questions we can expect. So every year paper, if you go and see, you might be already practice, you might be observed. So at least one question we can expect from the floating point area, we'll observe. So to understand the floating point area, little basics from the fixed point representation will focus it more. So as I mentioned, so this number representation you understand. So numbers are numeric and non-numeric will be there, right? Yes or no? This data representation goes. Let me write like this. Data representation, data can be. So data can be writing. I am writing the data can be non-numeric data, non-numeric and numeric data. Numeric, right? So numeric. So this numeric we classified basically into two types. One is fixed point. One is fixed point. Second one is a floating point. Floating point. Please understand. This fixed point also further classified into like integer and fraction. Integer or fraction. Getting my point? Fixed point integer, fixed point fraction. So if I say like fixed point, please understand radix point is fixed. Radix point is fixed, right? Yes or no? Radix point is fixed. Like example, if I take, so 123 is a number, integer number if I take, so radix position is what? So rightmost right. For fractions, leftmost right is there. So in this case, what happens? This radix point is moving. So moving across the digit here. It is not fixed here. It is moving across the digit. This fixed point can be unsigned or signed. It can be unsigned, it can be signed number. So same floating point numbers also, it can be unsigned, it can be signed here. Yes. So now little this representation, integer and fraction and floating point number. So three things will start representing. So let's, if I take, let an n bit number representing fixed point, signed, unsigned. Let me take first unsigned unsigned integer part, integer. If I take fixed point unsigned integer, so let me take like b, like b0, b1, b2, like this, bn minus 1, n bit number, n bit binary number I am taking, n bit binary number from b0 to bn minus 1. If you take any number system, please understand, any number system, it could be binary, it could be decimal, or it could be octal or hexadecimal. So any number system has two things. One is value expression will be there. Value expression, I hope you understand, right? Expression, value expression. And the range, second one is the range will be there. Second one is the range will be there. Yes, one is value expression, second one is the range. So what is the value expression for this? Value expression summation I equal to 0 to n, right? N minus 1. N minus 1 only? Yes or no? N minus 1. Each digit, if I take bi is each digit, you have to multiply its weight 2 power I. This is the value expression. Value expression. Range for this positive integer is 0 to 2 power of n minus 1. This you have to understand. So this you have to note it. Already you know. So this has a lot of applications. Like with this positive integer, many times other area also, not only this subject, even other subjects also, people ask questions on the range. Like suppose if I have n bit number, if I take 8 bit number, what is the range? What is the maximum number possible? 8 bit number is there, what is the maximum number, positive maximum number possible? Like with this respect, we can get signed numbers also. Unsigned integer range is what? 0 to 2 power n minus 1. There are two things you need to observe. One is value expression, second one is a range of a number. I hope you understand. So this is if I take unsigned. So same, let me take, let n bit number, n bit binary number representing the fixed point, unsigned fraction. So that is, you understand, a1, a2, a3, like this an. So n bit number, this is a binary number which represent in the fraction number. So good evening Nikhil, good evening. So the binary number I have taken, this is a fraction. So as I mentioned, any number system having the value expression, second one is the range, value expression, range. For this value expressions, I equal to 1 to n. So each digit ai should be multiplied 2 power of minus I, So fraction side we have to divide by the weight of the digit we have to divide. So that's what I express 2 power of minus. For integer side, so weight you have to multiply for each digit. So sum of all weight you have to take. Here also sum of weight I have taken, but understand this weight I have divided here. For this range, it is very important thing because applications, if you see floating point area, you have to observe 0 to 1 minus 2 power of minus n. This is a range, please note of it. Already you know 0 to 1 minus 2 power of minus n, where n indicates a number of bits, where n indicates a number of bits in this. Because n bit number taken, this is the range possible. With this a value expression for the unsigned fraction. See, integer I represented, fraction I represented. So next, these are two cases I took, no? This is the case number 2, right? So before case number 1. Case number 1, what I took? Integer, fixed point, both the case fixed point. Right? Example for this what? Example 123. So decimal number if I take like this, integer. This is what? Integer, right? If I take 10111 is a binary number, it is an integer like this. These are integer numbers, right? For this examples, right? Separate example 0.111, like if I take binary. So you understand, fixed point unsigned fraction. Fraction is binary point is leftmost side. For integer, rightmost side, that you know, right? So like if I take 1, 2, 3, the base decimal number, if I take leftmost side is there. So let us see the third case number 3. Case number 3, let n bit number binary number represents the so represents the fixed point signed integer. If I take signed, how signed numbers are represented? Signed integers. Yes, what are those? How signed numbers are represented? We have some mechanisms to represent. What are those mechanisms? Signed numbers means, example, see, I am writing integer only, I am taking minus 1 to 12, like the minus 12, like this. Suppose minus 1 0 1 0 1, like this. If I take, this is what binary. These are the signed numbers, right? This is a negative sign, like suppose it can be plus 1 0 1 0, like this. Understand, like this. How these signed numbers are represented in the computers, how they are represented? So you might have known already, right? There are three notations we have, right? There are three notations are there. So to represent the sign of a number are signed numbers, you understand. One is signed magnitude, signed magnitude. Second one is the ones complement. And third one is a twos complement. I hope you understand. There are three notations for representing the signed integers. Sir, normally can't we represent, sir? Normally can't we represent without these notations? Understand. Example, suppose. Example, if I ask you, all of you, please understand. Example, if I take like this. Example, if I ask you to plus 5 represent it. How to write plus 5? So 5 in a binary, what? 1 0 1, I can write it. Plus nothing but if you are adding plus. So how to represent? Suppose if I say plus is 0. Suppose plus is 0. So 0 you can add it. 0 I can add it. 0 we can add it like this. So this is a positive number, I can say. Similarly, if I ask minus 5, if I represent, minus 5 if I want to represent. So 5 you can write it, 1 0 1 I can write. So minus how to write? So we have some notation for representing these negative numbers. We have a representation, we have a three notations. We have some representation for negative numbers, these negative numbers. What are those, sir? One is sign magnitude, second is ones complement, third is twos complement. There are three notations are there for representing the sign numbers. In this case, in negative sign number representable, this positive sign also we can represent here by using them. So I hope you understand, right? So let's see some example for this. Example, look all of you. The first case is sign magnitude, right? Sign magnitude. Second notation is ones complement. Third notation is twos complement, right? Twos complement. Let's take example, if I want to represent 5. What this sign magnitude saying that? How we can represent plus 5 in a sign magnitude? Sign magnitude you read properly. Sign and magnitude is there. What is the sign? Positive. Please all of you understand. Positive, for positive numbers you have to represent as a 0. For negative you represent as a 1. In the n-bit number, leftmost bit we are dedicated for representing a sign of a number simply. Leftmost bit, you understand, MSB bit we call. MSB bit is going to be used for representing a sign of a number. If the number is positive, represent 0. If the number is negative, represent 1. That's simple thing. You see, sign is there. Sign, what is sign? 0. What is the magnitude? 5. 5 means 1 0 1, we can write it. When it comes to ones complement, so this also same. What is sign? Positive. So 1 0 1. So this also 1 0 1 only. Sir, why all three are in same? Why all three notations have the same? So you have to note of it, one point. For all positive numbers, all three notations are the same representation. There is no any changes. All three having same representation, like plus 0, plus, like plus 5, plus 5, plus 5. When it comes to negative numbers, suppose if I ask minus 5 represent here. If I ask to represent minus 5, how minus 5 is going to be represented? Same. What is sign? Magnitude. What is sign? Sign is negative 1 1 0 1. So sign is there, magnitude is. When it comes to ones complement, so you keep sign as it is. The magnitude is there, invert it. Invert means 1 becomes 0, 0 becomes 1, 1 becomes 0. That's like this. When it comes to twos complement you can obtain, right? Adding 1 to the ones complement, add it 1, it becomes 1 0 1 0 1, like this, you understand. See, for representing the negative number, we have three different notations or not? Three different notations are there. For representing the positive number, all three are having same pattern, that you have to understand. Now sir, which one is better among three? So which is exactly going to be represented in a computer system, in a machine instructions in a machine level, which format or which notation is used for representing the signed integers, signed numbers? So I can conclude that 2's complement is preferable. So you know, right? Reason. In a 2's complement, if you look at the range, in a 2's complement, look at the ranges. In a negative side, one extra bit will be there. In negative portion, one extra bit will be. That is the reason 2's complement preferable. That is the reason 2's complement preferable, ma. So now, so look at the point. So range. So range. Suppose I am taking the notation. And the range of this notation, range. So what is the first represented? Sign magnitude, right? Sign magnitude, please understand. Sign magnitude range. So sign magnitude, I am taking n bit number. So I am just taking what? N bit number. Okay, n bit binary number. What is a positive range for a have a n bit number? If n bit number if I take, what is the positive range? So just now we observe 0 to 2 power n minus 1. Only positive. But these notations are going to be represented negative numbers also. Some half of the distribution, like half of the number we have to give for negative side. So now you have to understand minus 2 power of n minus 1 minus 1 to plus 2 power of n minus 1 by minus 1. So this is very important thing, because some 1 mark questions we can expect in this area. So 1's complement range also 2 power of n minus 1 minus 1 to plus 2 power of n minus 1 minus 1. So third one is a 2's complement. 2's complement range will be minus 2 power of n minus 1. This minus 1 won't be there, plus 2 power of n minus 1 minus 1. Yes. So these are the three different notation. Their ranges are there. Because, so sir, what kind of questions we can expect here? Simply, many times I have seen him. 7-bit number if I use, under 2's complement representation, what is a positive maximum number can be stored? What is a positive number? Positive maximum number can be represented with a 7-bit number, they can ask. So if I ask, 2's complement, 2 power of 7 minus 1 to 2 power of 7 minus 1 minus 1. 2 power of 7 minus 1 is 6. So 6. So minus 64 to plus 63. Yes or no? Minus 64 to plus 63. In this case, minus 63 to plus 63. Minus 63 to plus 63 will come. So you see, here 64 is there, one extra number is there, right? That's what. In the computer system for representing the negative numbers, signed integers, we use a 2's complement representation. I hope you understand this point. Fine. So what we can do, some questions, we'll see some question, how number can be represented in a 2's complement, 1's complement and sign magnitude. Though you practice, so few example I want to take it. Here is a question. Represent the following number in 2's complement notation. Represent the following numbers in 2's complement notation. Because these are the sign numbers I given. These are the sign numbers are there. So we have a 3 notation to represent. So look this. Minus 12. How to represent minus 12? So there are two approaches we can do. So minus 12, look this, minus 12 is there. First we can get the sign magnitude. Of it. How to write sign magnitude? Very easy. Sign magnitude says that take the sign. What is sign? Like negative is there 1. Magnitude is there 12. 12 out right? 1 1 0 0. Bus. This is your sign magnitude. Fine. What is the 1's complement of it get? What is the 1's complement representation? Sir, 1's complement representation. 1's complement representation. 1's complement will be keep sign bit as it is. Remaining magnitude is there, right? Inverted 0 0 1 1 like this. How to obtain the 2's complement? Now? So 1's complement plus 1 you have to add it. What is the value will be there? 1 plus 1 0, right? 1 carry. 1 plus 1 0 1 carry, means 1 here 0 1 like this. So this is a 2's complement representation of a minus 12 here. 2's complement representation of a minus 12. So one approach is that whenever question been asked like no, given one number is there, if they ask you to represent 2's complement, simply first you write the sign magnitude, then get 1's complement, then get a 2's complement, right? No, writing sign magnitude, 1's complement, 2's complement. If suppose in some case integer is given, they ask to represent 1's complement, you can get it like this. So all three are given. Sir, can't we get directly, can't we get directly like this? So without converting into sign magnitude 1's complement, can't we get into directly 2's complement? Yes, we can get it. Let's work for minus 21. So now I want to represent the minus 21 into directly 2's complement without going to sign magnitude 1's complement. So how it can be done? How it can be done? Look this, minus 12 is there, minus 21 is there, right? Very simple method I will tell you to represent the minus 21 into 2's complement. So all of you please understand, this is I hope you already are practicing. So binary digits are there, those digits you have to remember their powers, their power you have to remember. Like example, first is what? 2 power of 0. So second bit position is 2 power of 1. So third bit position or third bit weight is 2 power of 2, like 2 power of 4, 2 power of 5, 2 power of 6, like this, 2 power of 7, like this is there, right? So what is this weight? This is 1, this is 2, this is 4, 8, 16, 32, 64, like this will be there. You have to remember 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, like this you have to remember. So that things will be easy for. So now minus 21 I want to represent, minus 21. So like just if you ignore minus 21 is there, right? 21 is there. So now if you look at the powers, greater than 21, where is the power is there? Where is the greater than 21? Suppose if you take 16, so 21 is greater, then 32 I have to go. So 32 is the greater than 21. Suppose if I plot it this here 1, so can I get this weight or not? If any position if you plotted 1, so that weight I will get it, right? So in a 2's complement, please understand one very important point already you know. In a 2's complement representation, the sign bit has a negative weight is there. Sign bit has negative weight. So that means you understand, the moment you plot it, so you won't get 32, minus 32 will get. Plus, I am adding some positive value x to get the minus 21. How much value I need to tell me? So to get this 21, how much I had to add for the 32? So 9 plus 3, right? 9 plus 2, 11. Am I right or not? 11 only. So 11 you have to add it. So 11 nothing but here. So this all positions are positive only. This only having the negative weight, this only having the negative weight, remaining are positive weight only. 11 I need. 11 means what? 8th position, 10, 11. So this position is 0, this position is 0. So this is a 2's complement representation of a minus 21. Directly. It is not required to convert sign magnitude representation, sign magnitude 1's complement, then 2's complement. Not required, directly you can represent this. What is the property you have to understand? In a 2's complement notation, sign bit has a negative weight. Then how to do? You look at the number, just go to next greater position, plot it that value, will get a negative weight, some positive value, add it, you will get the, add it positive value, you will get the value. So that means how much x value to represent, then you can represent it. So what is the next one they asked? Minus 43. Let's try for minus 43. So minus 43, yes. What I should quickly write? Powers, 2 power 0, 1, this is 2, this is 4, this is 8, 16, this is 32, 43 means next I need 64. So you plot it 64, what you will get? Minus 64 you will get, right? For this some positive value you add to get the minus 43. How much you have to add? So 7 means 17 plus 21, you can do it 64, 43, this is 1, this is 21, yes 21. So these are the area is what? Positive area, right? SR positive weight. This is a negative weight is there, negative weight is there. So 21 you have to add it. 21 how to get? 16 plus 4, 20, this is 1, right? Yes or no? This is positions are 0, this is position 0, yes. So this way you can get it directly, yes. This way we can expect the question. Sometimes we can get the reverse also. They'll give the binary 2's complement number. They'll ask what is the decimal equivalent to 2's complement binary, they can ask. So let us work out that one. So find the decimal equivalent to the following 2's complement binary numbers. These are the numbers which are not normal binary numbers. The mentioned 1, 2, 3, 4, right, which are not normally binary number, which are 2's complement represented number. They are asking what is the decimal number. They are asking what is the decimal number. Very quickly, you might have practice, but try to minimize the time to apply some shortcuts. So how we can minimize, sir? This number is there, 10101101001 is there. So this is 2's complement. We need to get what? Decimal number. 2's complement of a 2's complement, what is the value? 2's complement of a 2's complement, you will get a sign magnitude, right? You will get a normal number. So that is one approach. That is one approach. Other approach is simply, please understand. Other approach I will tell you, directly I will tell you. So what I am trying to say, take this number 101001, right? So you see the number, just look at this one is there, this weight I have to consider, this one is this weight I have to take, this weight I have to take it, right? What is the weight? 2 power of 0 means 1, this is 2, this is 4, 8, 16, 32. As we know, if the number is in 2's complement, its sign bit position is having a negative weight, right? Minus like this. So minus 32 plus 8 plus 1, that's what I understand. What is all 24? Minus 24 means minus 23 it is representing, right? Yes or no? Simply again for this also same thing you have to do it. What is the number is there? 1 1 0 1 1 is there. This weight is 1, this is 2, 4, 8, 16. Which is 16? Minus 16. So this is, you understand. So minus 16 plus 8 plus 2 plus 1, right? What is this value? 10 minus 6 means minus 5. It is representing minus 5. Yes, minus 5 only? Minus 5. Yes. So similarly, what about this? What about this? So if I take this number like the question 3, 1 1 1, 3 ones, 4 ones, 0 1 1 0 1 is there. What is the weight? 1, this is 2, 4, 8, 16, 32, 64, 128, 256. So minus 256, right, plus 128 plus 64, right, plus 32 plus 8 plus 4 plus 1. Okay, this computation you need to do. Yes or no? This computation you need to do. So minus 256 plus 120, that all you have to do it. So one more things we need to observe here. One more thing need to be observed here carefully, all of you. So what is need to be understand? I will tell you. Look this, all of you. Look this, all of you. Example, plus 128 is there, positive number is there. Simply I will take 128 only. 128 only. It is how many digits are there? If you take decimal number, 3 digit number. If I ask you to represent in 5 digit number, if I ask you to represent this 3 digit decimal number to 5 digit, how you can write it? Simply you will pad it, 2 zeros 128, right? It is at 5 digit or not? Yes or no? Yes. Suppose if I ask you minus 125 is there, this is a decimal number, then see. Now, if I ask you to write in 5 decimal, there are 3 decimals are there, I ask you to write the 5 decimal, then we will get a confusion. What is confusion? Sir, negative number is there, how to represent, sir? Negative number is there, how to write it? So that is a difficult, right? So now you understand. Now you understand. When you are extending, like when you place a smaller number in larger register, so this we call, extension process we call. So I hope you studied. So you know, right? So 1's complement, 2's complement number I can represent it for this or sign magnitude. But you have to, this number I want to place a larger register. So what about sign? Sign need to be extend. How to extend, sir? Simply you understand. Sign bit whatever it is that you copy to remaining extended position in case of 1's and 2's complement. Note of it. If you are using a 1's or 2's complement notation for representing the signed integer, when you want to extend, when you want to place that number into larger register, the sign bit is there, whether 0 or 1, simply you copy all the extended position. That's what representation. In case of sign magnitude, the sign bit will be moved to leftmost position, remaining extended positions are filled with zeros. I hope you know this point. So now you are observe here. So here you just if you look at this number, here in left to most side, since this is a 2's complement number, leftmost number if you see 1 1 1 1 4 ones are there. So by looking this you understand there is a small number is there, it might be, it is what stored in larger register. So that I am writing here, here I will write it, here I will write it, here I will write it. So what is the number was there, what is the number? 4 ones 0 1 1, 4 ones 0 1 1 0 1, right? This number is there, 0 1 is given, okay. So by looking this, what I able to understand, I am looking the leftmost bit, this leftmost bit is a MSB bit. Since it is 2's complement number, sign number only. You understand this bit is copied from here only, this bit is copied from here only, this bit is copied from here only. Means 101101 is this is original number actually. This is a original number, small number, placed in large register. So how you able to understand? This bit only copied many extended positions. I mentioned now. Under 1's or 2's complement, sign bit is simply copying only, copied. So it is not required to evaluate this all the things. It is not required to evaluate. You evaluate the original number only. So what is the values positions? This is what 1, 2, 4, 8, 16, 32, minus 32, minus 32 plus, minus 32 plus 8 plus 4 plus 1. So this value almost 10. Like suppose if we take so 12, right, 20, minus 20, minus 19 represents. If you evaluate here, this also you will get minus 19, this also minus 19. So the sign extension process neither change the value of a number nor sign of a number. This you have to understand. So with this respect, look at this fourth one, you tell me what is the value it representing. So it is not required to evaluate all the bits, ma'am. You have to understand this is copied from this all the locations. Here is understand this only original number here. So original number is 1011. I am writing here. Original number is 1011. So this you have to evaluate. This is what? 1, this is 2, 4, 8. Which 8? Minus 8 plus 3. Minus 8 plus 3 is minus 5. So you understand minus, this is the whole big number representing minus 5 only. So that means understand small bits, smaller number bit represented stored in larger size register. So in that case, sign bit simply you have to copy it all the locations. So I hope you understand sign extension process and also how to get the decimal equivalent to the 2's comp binary number, because couple of papers I've seen, they given a binary number which represent the 2's comp representation, they ask you decimal. So this way you can do it. So what is the property you would understand? So in 2's complement numbers, sign bit is having the negative weight. That's all. Evaluate it. If the many ones are there, you try to find out the original number by removing the copies. Then that part only you evaluate it like this. No? There are two things. Here also you understand. This bit is copied from here only like this. Original number this much only. If you evaluate this also, you will get same answer only. What is the minus 5 only, you will get it. So this also copied from from here like this. This also copied from here. That way you have to understand. So this is all about fixed point number representation. So there are three things we need to notice. Integer range I have given 0 to 2 power n minus 1. Fractional unsigned range I have given 0 to 1 minus 2 power minus n I have given. Fine. And these are the unsigned part. Signed part represented by sign magnitude or 1's complement, 2's complement. Their range is also given. Their range also given. This part over. So now let's move for the floating point number representation. Floating point number representation. Fine. Now look at the floating point part. So floating point number representation. So why do we need a floating point number? First of all, why it is required? Why it is required to move for floating point? So first thing you have to understand, real numbers are there. Real numbers, suppose 12.5, 12.43 like this. In this case, decimal point is not fixed one place. It is moving across the digit, right? To represent these real numbers, we need some format to represent. First thing. Second thing you understand, range of a representable fixed point numbers, range of representable for fixed point numbers is restricted. Why it is restricted, sir? Example I will tell you. If I ask you 8-bit number is there, if a 8-bit number is there, what is the maximum number you can store in 8-bit number? 0 to 2 power 8 minus 1, right? That is 255. If I ask you 16-bit number is there, In a 16-bit number, what is the maximum number you can store? 0 to 2 power of 16 minus 1. Yes or no? 2 power 16 minus 1. So this is the size you can get it. So this range may not be sufficient for many scientific applications. I hope you understand. The range of a representable in a fixed point notation may not be sufficient for dealing with the scientific applications. I need so different way. Means I cannot increase examples. So from 16 to you can go 32. Today we have 64. But behind that you cannot represent. Behind that you cannot increase, right? So that size is again limited. Now you understand. Floating point number is saying that even if the number is representable, it is convenient to express a number like this large number you can express into 1.0 into 10 power of 6. I can write it or not. This is the format of the floating point. Floating point have a convenient mechanism to represent in a larger integer number, although again as well as and real numbers also can be representable. So let us, so you have studied already, but let's recall what the format of the floating point number and how we can number representable, that we can see. Look this, the computer system designers implement a built-in data type of a real numbers in a floating point representation. This real number n can be expressed as n equal to m into r power of e form. You have to represent number into what? M into r power of e. This format you represent. So what is this e, sir? E is a exponent. The e is a exponent. M is what? Mantissa. M is what? Mantissa. M is a mantissa. So any number, please understand here, the large integer number or real numbers we need to convert into this format, m into r power e format to represent. Now m and r explicitly stored in the memory. R is considered to be with the design only. R is a base of the system. What is R here? R is what? Radix. Radix are base of the system. Base nothing but if it is a binary number 2, if it is a decimal number 10, if it is octal numbers like 8, like this, you understand. So now this floating point number can be a negative positive, right? So I am keeping like plus or minus. So plus or minus m into r power e format you have to represent. So that means you understand here the floating point number has a two formats are there, two parts are there. What are those? One is exponent field is there, another is mantissa field. Exponent, mantissa, there are two fields are there. Getting my point? Exponent, mantissa. I am writing. So floating point number representation has the two parts. One is mantissa. One is mantissa. Second one is what? Exponent. Second one is a exponent. Exponent. Fine. Look, all of you. This mantissa is can be integer. Please understand. It can be integer or fraction. Integer or fraction. Please understand. Exponent is integer only, but this integer can be two things. One is signed. It can be unsigned. Getting my? It can be signed. Exponent is an integer only. Integer can have a signed integer or unsigned integer. And mantissa is a integer or fraction. It can be integer or fraction. But most of the practical cases, mantissa we know fraction only, fraction format only. So let us take an example. Let us take an example. Look this example, all of you. Look this example. So if I take a number n is there, 6. Look, 624.546 is there. 5467 is there. This is the number. Which number? Decimal number I am taking, real number. What I said, every number you have to conveniently express into m into r power of e form. So this we need to be expressed like this, What I will do, this I will shift like decimal point I will shift left side. So 0.6245467 into how many times shifted? 1, 2, 3 times shifted. When I shifted 3 left to shift, arithmetic left to shift indicates what? 3 times you have to multiply base of the system. What is the base of the system? 10. 10 power of 3. So you understand? So this is a mantissa or not? M or not? Tell me. This is the E. What is E? Exponent. What is this? Radix R. Base of the system R. Like this. So now m into, see, m into r power e form is there, right? M into. So now what number we have to store in a computer system is 6245. So 6245 467 comma 3. These two numbers only we stored. So this 10 is there, right? 10, the base of the system 10, or binary decimal point is not stored specially. We are not storing. Why, sir? Because the designer, like a hardware itself supporting. I said now most of the practical cases Mantissa we are assuming as a fraction only. We are treating by default fraction. And if I design the binary, base of the system is by default 2 only. So it is not required to store explicitly. Only explicitly you have to store exponent and mantissa, that you know, right? So now, so what is the expression I can write? So this number also I said now there are two things will be there, right? One is value expression will be there, and second one is the range will be there, right? Value expression and range will be there. What is the value expression I mentioned? M is there. M is a what fraction I said into r power of e form is there, right? Yes or no? So now this mantissa can be positive or negative, right? Plus or minus point m into r power of e form will be there. Fine. So since I mentioned e is the exponent, what is e? Exponent. Okay, exponent, right? Exponent can be, right, as you mentioned, the positive, it can be negative, means signed integer or unsigned integer. There are two things are there. So to represent this one, this number, when the exponent is having the signed and unsigned, definitely I require some notation to represent, right? Yes or no? What are the notation we have? Side magnitude, or we can use 1's complement, or we can use the 2's complement, right? So which is preferable among 3? 2's complement. The fourth one we have excess n form. I hope you understand excess n form, right? Excess n form, biased form. So you might have learned. So excess n form. So we are preferring among 4, excess n form is preferring, biased form. So biased form saying that when the exponent is positive or negative, during arithmetic operations, it is create a lot of, trouble, nothing but alignment problem is more. You might have know the reason, when you have a exponent field, positive and negative is there. Whenever I want to do the floating point arithmetic operations, one exponent is positive, other exponent is negative is there. We have to do this alignment. So alignment requires a lot of operations. To minimize this speed up, to minimize this operation, what we can do, so this entire exponent we have to convert into positive side only. That's what excess n form saying that. So we have to represent in terms of positive form only. So what we have to do, this exponent, something we have to add, some bias value. So that we are storing in a capital E. So now you understand, it is a original value, right? Original exponent. It is a original value, right? This is what, please understand. Biased exponent we called biased exponent we called. I hope you understand. It is a biased exponent, original exponent. For this original exponent, we have added some bias value so that we got a capital E. So capital E you have to store it in a computer, not small e. Small e we should not store. We have to store capital E. So while retrieve, what we can do, the bias can be removed from small e. So bias can be removed from capital E. You can get the original E. So this thing you know, right? So now we are storing capital E, not small e. So now I can write the modified thing. Look this. So now what I can write, small e, to obtain the small e, from capital E you can remove the bias, right? So now value expression goes like this. Value expression goes plus or minus point m into 2 power of bias e, right? E nothing but capital E minus bias I can write it. So both are same only, right? See, 2 power e nothing but in terms of bias is there. The final expression I can write. So plus or minus, what I will do? So I will write minus 1 whole power of s, right? S means sign bit into, this is m, point m. It is also base 2 into 2 power of e minus bias. So this is the expression. This expression we called explicit normalization. Explicit normalization equation you can say. So I hope you know this. What is the meaning of normalization? Generally, why we are moving for normalization? The mantissa bit is there, mantissa bit. Getting my point? Mantissa bits are there. This mantissa bit, so this mantissa, what I said, any integer or fraction is there, we have to convert into fraction form only, this form. So m into e 2 power of r e form you have to express it. So mantissa is practical cases fraction only. But when you make it into fraction form, what happens, they can start with the leading zeros. That leading zeros, creates in multiple patterns. To avoid the multiple patterns, what we are saying that we are saying the normalization. Normalization, a process of eliminating the leading d zeros from the mantissa. So means this mantissa has start with what? 1 only in case of binary. This has to start with 1 only in case of binary. So I hope you this you know. And somebody give me what is the implicit normalized expression for this? So implicit normal expression for this value expression equal to -1 whole power of s 1.m base 2 into 2 power of e minus pi r. I am taking the equation number 2. Equation number 2 indicates what? Implicit normalization. In the question, if they mention implicit normalization, if they given, you have to use this expression. In the question, implicit keyword is not given, you have to go with explicit normalization. So this we need to understand, all of you. So these are the two equations, equation 1 and equation 2 are important, very important things, you need to get it. So now one limitation is there. It is a YouTube live. Sorry for the disturbance. Okay. So there are two important things you have to understand. If suppose from floating point area two areas where we have, there we can expect the question. One area is what? The basic of floating point implementation or conventional methods for conventional approach for the floating point implementation. So means before IEEE standard came into 1985, implementation start with 1990 onwards only. The before that, how floating point number represented? This format only, explicit, implicit. Now for storing the register, let me take one more slide. To store this floating point number, as you know, right, the register is divided into three parts. One is sign bit is there, other is exponent is there, if I take k bit here and mantissa will be there. So now this is a format for representing or storing the floating point number, right? Register having three things: sign bit having 1 bit, exponent is k bit, m is mantissa. As I mentioned, right, explicitly floating point number which we store in the computer system, exponent, mantissa only. So entire thing we won't store, like base of the system or decimal or binary point we won't store. We will store only exponent, mantissa. I hope you understand this one. But conventional or traditional approach having some limitation. What is the limitation? 0 you cannot represent, and this number distribution is not continuous. It is a discontinuity is there. Means already you studied, right? Any two consecutive numbers, if I observe, there is a lot of gap will be there. So take any two consecutive number which are represented here, you check the gap between any two consecutive numbers, you will get a lot of gap. That's what I can say. Conventional approach, it is not continuous. It is a discontinuity is there. The lower level, overflow, underflow problem is there, right? To solve this problem, IEEE institution, please understand, IEEE institution has given a standard for representing the floating point number. The standard name is what? 754. So I can write IEEE 754 floating point standard, floating point standard. And most of the modern architecture is incorporated with this standards. You understand? So modern architecture, if I say, for representing the floating point numbers, IEEE 754 standard being used. So before this standard was not, normal conventional, conventional traditional approach was used to use. Example, IBM system if you take, so a 16-bit architecture, 16-bit or 32-bit architecture, if you see, mantissa and exponent fields are having different sizes, but they are fixed here. Under this standard, every field have separate bits, exponent field is fixed and mantissa field also fixed here. So let us observe about this standard. IEEE has sponsored a standard of single precision and double precision, both are there. Even extended precision also there, that is having the 128 bit mom. That is having 128 bit. The floating point number can be represented either in implicit normalization or fractional form, which you know. It gives a provision for representing the plus or minus 0, plus or minus infinity can be represented by reserving some certain patterns of the mantissa. As I mentioned, conventional method or a traditional method where you cannot represent the 0. Reason you know, right? Reason means normalization saying that mantissa should not start with 0. If it is start with 0, we have multiple patterns. So mantissa should start with 1, minimum bit should be 1. When you fix it 1, minimum number is 2 power minus 1, 0.5, you cannot represent 0. So we don't have provision to represent 0 in a traditional approach. That's what it has a problem, lower underflow as well as overflow problem is there. So that can be resolved here. It gives a provision for representing the plus or minus 0, plus or minus infinity. This is not the plus or minus infinity, by reserving certain patterns of the mantissa and exponent. And some combination of the mantissa exponent does not represent any number, that we call nan. Even it is cannot be representable. Example, root minus 2 if I take 0 by 0. So 0 by 0, this cannot be representable. That's what we are representing as a nan. So let's observe. So this the standards, they have two standards we have there. So what I am trying to say now, IEEE 754 standard has given a two, it is sponsoring what, two standards. One is 32 bit one we call single precision, and second 64 bit one we call double precision. Fine. So in the register size 32, here register size is 64. Even we have a extended one is 128 is there, 128 bit. But in our syllabus 32 being asked all the time, we got a questions from 32 bit only, not from 64 bit. So let us see the 32 bit format. What I said you, this is a register. This is a register, you see. So register, we know three parts are there. One is sign bit. It is 1 bit is fixed. Exponent I said k bit. It is fixed here, 8 bit here. And mantissa here 23 bits are fixed here. 23 bits are fixed. Getting? 23 plus 1 24 plus 8 24 32. This is fixed here. Now conventional approach you might be studied, their bias value is to change, depends on the register size. Suppose 32 bit register, some bias will be there. Under 16 bit register, some bias is there. Here the bias is fixed, please understand. Here is a bias is fixed. Bias is 127 is fixed here. Bias is 127 fixed here. So other things will observe for this. So exponent field is given 8 bit are there. So what is the range you will get? 0 to 255, right? 0 to 255 range. Am I right or wrong? 0 to 255. Now you understand this E, capital E, unsigned biased exponent, E0 and E255 is reserved for special numbers. What are the special numbers? This is reserved for special numbers. Special numbers. What is the special number? I want to represent 0, I want to represent even large number, that is what infinity. That's what these two patterns are reserved. Now you understand the capital E is available for normal numbers, it will be 1 to 254 only. So this one range. Normal numbers, normalized number can be represented from 1 to 254 only. So this is one thing you would understand. Since here normally bias value is 2 power k minus 1, right? Generally 2 power k minus 1, right? This only, right? But some cases we can take 2 power of k minus 1 minus 1 also we can take it when I use for 1's complement to sign magnitude, right? So now here is a bias is fixed, right? Bias is fixed. Bias is how much? 127 is fixed. What is the true value? True exponent. Small is what? True exponent. Now please understand what is the maximum exponent can possible. True exponent. Please understand. True exponent, what we are true exponent, for this we are adding bias, right? Bias. We will get the capital E. We will get the capital E, right? What is the capital E range we know? 1 to 254. So if you want to store maximum value, how much maximum? Here bias is fixed, 127 is fixed. Now how much maximum possible? 127. 127 plus 120 is how much? 254 only, right? So now you have to understand. Maximum capital E will be 254, means true exponent. Please understand, your user giving the numbers, right? What is the maximum exponent field you can give? 127. So for which you are adding 120 bias, total will be 254. Sir, what is the minimum value can be done? So it is 127 only. So now see, what is the minimum of this one? Minimum is 1. Now to get the minimum of 1, how much I can be? It can be minus 126, please understand. Minus 126 plus 127 is 1 or not? So this is a minimum value. So that means you understand, small e range is minus 126 to 127. What does mean here? Very small number can be representable or not? Smaller than small number. 2 power of minus 126 is a very small number or not? 2 power of minus 126 range, if I take it, positive range is what? 2 power 127 is a large number. Negative side 2 power minus 126 is small number. So that is possible to represent here. So this we call the D normal number. When you represent smaller number, nothing but D normal number we call. This is what? D normal number. So IEEE 754 standard also given provision for storing the smaller than the small number, larger than the large number. So that you can observe here with this. Fine. I hope you got the meaning of the capital E and small e. Capital E and small e. Fine. So now similarly 64-bit also we can observe, but 64-bit, we don't have a syllabus, better not to revise this one. If you want to know, I can tell you, with 64-bit case what happens here. 64-bit segregation goes, one sign bit 1 is there, for exponent is 11 bits are there, mantissa will be 52 bits will be there. So in this case bias value will be 1023 is fixed, it is fixed here. Like that you can observe. So let us see the how normal number can be representable, how 0 is representable here, how large number, negative number, like now example if I say how we can represent the like the infinity number, those format we can observe. So first I am taking the single precision as a 32-bit now. 32-bit single precision I am taking, and look at the segregation. Since I told you, so this has 3 things, right? One is sign bit, S value I am taking as a sign bit, and exponent is at 8 bit is there. Then mantissa is what? 23 bits are there. Let me represent the value. What is the value it is representing? So I will write in terms of case wise. Case number 1, the sign bit can be 0 or 1, right? Positive or negative. So sign bit can be 0 or 1. So when it comes to exponent, 8 is there, right? 8. E value, please understand. First case I am taking. If E is 0, exponent field is 0. This M is 0, means all bits are 0. This value representing plus or minus 0, it will represent. As I mentioned all of you, IEEE 754 standard giving the provision for representing the 0. So what is the standard? This one. E must be 0, M must be 0. Then this representing what? 0 representable. Case number 1. Case number 2. Case number 2. It can be 0 or 1. Now see, understand. If E is full, this is E is full, nothing but what is E? 255 only. This M is 0. This is M is 0. This will represent the plus or minus infinity. Plus or minus infinity represent. This is what case number 2. So look at the case number 3. Case number 3. Sign bit 0 or 1. Sign bit 0 or 1. Now 2 case special. These are special numbers over, right? Now E is available from 1 to 254. When it's 254, M can be anything. Please understand, any combination. This represents the implicit normalization. Implicit normalization. I will give the expression for that. This will represent the implicit normalization. Case number 4. Case number 4, 0 or 1. Now understand. Case number 4. This exponent field completely 0. Now mantissa not equal to 0. Not equal to 0 means something is there. This represents the fractional nothing but D normal number. So D normal number represents this. Case number 5. These 5 cases, if you understand, answering questions from this area becomes very easy, all of you. Case number 5. If E is full, 255, getting my point, and M is not equal to 0, this will not represent any number. Nan we call, not a number. This meaning not a number. Now we have all the cases. This pattern for 0, pattern for large number, pattern for normalized number, pattern for denormal number, pattern for not a number. So these are the 2 things we need to get it, like for this 2 cases we have. For representing a normal number, this is a denormal number. So I said you like implicit normalization. What is a implicit normalization expression? Expression. In this case, value expression will be, as we know, same will be there, little change, -1 whole power of s. Implicit nothing, 1 point m base 2 into 2 power of e minus bias. Bias is fixed, right? 127 is fixed. This is the equation for that. This we have to see. This we have to use it for. So fractional form. Fractional form nothing but denormal number. Denormal number value expression is -1 whole power of s fraction, right? F. M you can point m you can write it. F I am writing just into 2 power of e. Now tell me e. What is the e? Minimum e. Minimum e possible how much? E minimum how much possible? Capital E. 1 only, right? 1 minus 127 was -126. This is a minimal number you can represent it. With this number, normal number nothing but if E is, you take large number. So E is large, what happens? 2 power of 127, right? That large number you can store. This is a minimal number, you can store it. So there are 2 things we have. One is a normal number, denormal number expression. These 2 things you need to use for solving the questions. So sample, I'll solve one question here. Consider 32-bit register that is used to store the floating point number in a single precision IEEE 754 format. Compute the value given by the register. The register given 32-bit. So there are 32 bits are there. They given. They asked decimal value too. So one thing you would understand, all of you, question, please, question can be framed like, they can say single precision, sometimes say they can say 32-bit is simply they can say IEEE 32-bit. Indication single precision only. Sometimes they won't give 32-bit. Simply say IEEE 754 single precision, meaning itself 32-bit. Now we know, right? So left to most bit is yes. Next 8 bits are exponent. Next to 23 bits are mantissa. How many? 1, 2, 3, 4, 5, 6, 7, 8. 8, right? This is exponent. This is mantissa, right? Yes or no? So S value how much? 0, positive number. E value how much? 1, 3 zeros followed by 00, 11. 8 are there. 8 are there. Tell me this decimal value for this. What is the decimal value? This is 1, 2, 4, 8, 16, 32, 64, 128. So 128 plus 3 how much? 131, right? 131 is a decimal, right? So exponent we got 131, nothing but is a normal number only, normalized number only. So write the expression, value expression. What is the value expression you have to use it? -1 whole power of s, 1 point m implicit normalization into 2 power of e. E how much you got? 131 minus bias is 127. Fixed, right? Yes. S value how much? 0. So -1 whole power of 0 positive, 1 point m. What is m? M is given here. 1.100, many zeros are there, into 2 power of e. 131 minus 127. How much it will value give? This is 4, right? Yes or no? Then simplify it. Simplify this one. So what you got? This value will be positive only. You got like 1.1000, like n number of zeros. N number of means for 23. 1 is 22 zeros will be there into 2 power of 4. 2 power of 4, right? So can I shift left to side, right side? Can I shift it 4 times? How much? 1 time, 2 time, 3 time, 4 time. 1, 1, 3 zeros, right? This you will get the binary number directly. What is the value it is representing? What is the value it is representing? 1, 2, 4, 8, 16. 16 plus 8 almost 24. So positive 24 is the answer for this question. Since S value is 0, positive number. If S value is 1, that is a negative number, it will come. I hope you understand. See, from this like IEEE 754 format, if the question is framed, you are able to answer it, ma. These are the 5 points you have to understand. 5 points you remember. Understand, not record to remember. This is important things. Based on this only question can come. Fine. So now let's move on to the computer arithmetic. Computer arithmetic. So that's what number arithmetic. Okay. Number arithmetic. So what are the things need to be focused here? Under number arithmetic, what are the things need to be focused? So number arithmetic associated with addition. Getting addition, right? Second one is subtraction. Subtraction, right? Third one is what? Multiplication. Multiplication. The fourth one is a division. Okay. From this area, what type of question we can expect? From this area, what type of question expect? Most of the time which I observe, they are checking. Suppose two numbers you want to compute, addition. If I want to do two same signed numbers, I want to addition. Then whether you will get a overflow or not. Overflow condition majorly they are checking. Example, see, when you add two different signed numbers, there is no question of overflow. Getting my point? Subtraction cases we may not get the overflow. Addition case is possible. Multiplication case is also possible. And division case overflow is not possible because your dividing number will be small only. So now you understand this operation can be, please understand, each operation can be unsigned. Unsigned. It can be signed. Numbers can be signed or unsigned. Like unsigned addition, unsigned addition. So like an unsigned subtraction, unsigned subtraction, multiplication like this. Understand? See, addition unsigned, there is no problem at all. Unsigned addition, maybe positive addition only, no problem at all, because simply overflow comes. What you can do, simple thing what you can notice, suppose size is, you see the n bit number. So if those numbers able to fit in that range, fine, otherwise overflow, that we can get it. So when it comes to signed number, we need to little focus here. Two signed numbers we need to focus, because overflow. Suppose example, signed numbers if I take, two same signed number if added, there is overflow. Minus minus you can add, plus plus you can add, there is overflow. Need to look, we need to understand. When it comes to subtraction, like subtraction is there. This subtraction what they would do, like suppose example, a minus b is the subtraction. So this is carried out like a plus minus b only. A plus minus b. Minus b means what, sir? You can represent 1's complement, 2's complement, right? Or sign method you can represent and perform the addition. Fine. So means you understand, subtraction is carried out through addition or hardware only. Subtraction is carried out through addition hardware only. So multiplication case, unsigned case, no problem at all. Signed case, problem will be there. So we are not looking for a division, because most of the time we have seen division oriented questions we won't see. We did not see. Fine. So now major concern for us what? Signed additions. Getting my point? Signed subtraction also. Signed subtraction nothing but, see, understand. Two signed numbers you subtracted nothing but through addition only you have to do it. But still signed value is there. Signed numbers are there. So wherever right mark is there, like no, signed addition, signed subtraction, signed multiplication need to be worried. Fine. So now what type of questions we can expect in this area? I mentioned. So there generally they ask for testing what? Overflow only. Suppose two signed numbers added, I performed addition and subtraction, whether it is overflow or not. Otherwise they'll ask like no, what are the conditions to check this overflow? This kind of question they can ask it. Now major concern was signed numbers only, right? So I said you right, we know right. Signed numbers are represented by some notations. What are the notation? Signed numbers can be represented by 1's sign magnitude, 1's complement or 2's complement. There are three notations are there. So, 3 notations cases we can represent a number and you can perform addition, subtraction or multiplication. But multiplication some different thing will be there. So, you might have studied Booth algorithm. So, we are so this can be resolved with a Booth algorithm only. Normal multiplication cannot be used for the signed integer multiplication. Normal integer multiplication is there which you apply for unsigned integer. So, that will not extend or that will not work for the signed multiplication. Separate algorithm required to deal with them. That is what Booth algorithm is there. But recent papers we won't see the question from Booth. The previous papers we used to get it. So, from like if I observe past some 10 years, past 10 years paper if you see, there was no any question from Booth algorithm. Majorly they framed from addition, subtraction with signed integers only. So, we have to test it, what are the condition for checking the overflow here. Look carefully here. So, how to detect the overflow condition? How to detect the overflow condition? When I added two different signs, see when I added two same signs, when I added two subtracted two same sign, means please understand, there are two different signs if added, there is no question of overflow, plus minus, the value will be less than your range only. So, when you added same signs, there is a problem. So, these signs numbers are represented sign magnitude or 1's complement or 2's complement, you know, right? Sign magnitude, 1's complement, 2's complement. Let us see. Suppose if the signed numbers are denoted in the sign magnitude notation, suppose sign magnitude notation if I use it, the presence of carry out 1, so carry out 1 at the sign position denotes an overflow. When you added two sign numbers under sign mag notation, if you get the carry bit at sign position, that indicates the overflow. So, we know already in a sign magnitude arithmetic, sign bit is not participated in the computation. What does mean? Suppose when you perform the sign magnitude numbers addition, sign bit you will represent, right, in a sign magnitude. So, that will not involve in a participation in a computation, that is it. If this something comes under that position, that indicates the overflow. Sir, how to understand this one, sir? Example, I will take it. Example, minus 80, minus 70, I want to represent, ma. So, I want to add it, two same sign number. What is the value? Minus 150, right? I want to perform the addition of the two same sign number. So, let me take the 8-bit number. Let me take the 8-bit number, 8-bit register, 8-bit register. Okay. All of you tell me, 8-bit number if I use, what is the minimum maximum range we can get in case of sign magnitude? Sign magnitude range with this 8-bit number is 2 power 8 minus 1 minus 127 to plus 127. This is a range. Yes or no? This is a range. 8-bit number. So, 2 power of 8 minus 1, 7. 2 power 7 how much? 128 minus 1, 127. Minus 127 to plus 127. This is a range of a sign magnitude. In 1's complement also same range. In a 2's complement, here 1 extra will be there. Minus 128 to plus 127 will be there. I hope you understand. Fine. So, by looking this range, you can tell, sir, if I add these two numbers, there is a overflow only, because 80 plus 70 is 150. 150 you cannot fit into in this range, overflow only. But how hardware is going to be deducted? So, let's represent minus 80 into sign magnitude. I am using what? Sign magnitude. Why? Look this. How to write the minus 80? So, sign magnitude is saying that first you write a sign. Write the magnitude. What is the magnitude? 80. 80 how to write? So, 64th position, 64 plus how much I have to add? 64 plus 16. 64, 32 position 0, 32, then 16 position, 16, 8, 4, 2, 1 like this. 70, minus 70, minus 70 how to write? 64 plus 6. So, 64 plus 60, this is a 64 I will write. 64 I will write. 64, 32 0, 8 0, 16 0, then 16, 8 0, 4, so sorry, let me write, check the file. 64, 32, 16, 8, 4, 2, 1, 64, 32, 16, 8, 4, 2, 1 like this, understand. Is it 8-bit number? 1, 2, 3, 4, 5, 6, 7, 8-bit number. Yes, I am adding like this. Add 0 plus 0, 0 plus 0, 0, 0 plus 1, 1, 0 plus 1, 1, 0 plus 0, 0, this is 1, this is 0, 1 plus 1, 0, 1 carry. Please understand, these are the sign bits. Please understand, these are the sign bit. These sign bits are not participating in a computation, that you would understand. If I use this mechanism to represent the sign integers, so this will not participate under computation. You cannot add 1 plus 1 something. You cannot add it. It won't involve. Otherwise, in a 1's complement, 2's complement, they involve. In this case, it won't involve. Now, we got a carry right here. This indication what? Overflow simply. Anyway, integer level I observed, this it won't fit in the range. We can declare the overflow. But how we are detecting? This way I am detecting. So, this, like I mentioned, you read it, no? I said, no? Presence of carry out 1 at the sign position denotes an overflow, like this, you understand. So, this mechanism I hope you understand. Suppose if I use 1's and 2's complement notation for represent sign integers, then when I perform the addition or subtraction operation, how to detect the overflow? So, I will show you now, see. So, if 1's or 2's complement notations are used, then overflow is detected by one of the following two conditions. Two ways we can detect. One is numbers are of the same sign, and the result is opposite during the computation, then it results in overflow. The carry in bit into sign position and out of sign positions are not the same, then also results in overflow. Two ways you can detect. Either you see both the signs are there and result is opposite, then also you can say overflow. Otherwise, sign out and sign in both are not same, then also overflow. Two conditions are there. Based on these two conditions, many times question have been framed. So, how to take the condition? First condition, please understand. How to write the condition? Example, I will write it like A equal to, suppose Z is there, Z equal to A plus B I want to perform. A plus B I want to perform. I am taking. So, ZS comma AS comma BS are the sign bits of Z comma A comma and B respectively. I am taking sign bits. So, what I said the point, when you perform, please, what I said the point. So, A and B, AS and BS will be there, right? Like A, other things also there. When you add it, the Z is, this result is Z, opposite is there, then is a overflow. How I am going to detect? Look this. I am taking the AS, here is BS and ZS I will take it. Okay. Now overflow condition I am writing. Overflow. How I am going to write this expression? See, if AS bit is 1, BS bit is 1 and ZS bit is 0, then is a overflow like this. If this is 0, this is 0. If it is 1, this is also overflow like this, you understand. When the same signs are added, result is opposite side, then is a overflow like this, you understand. How to write the mathematically this? Function of, I will write AS comma BS comma ZS equal to, look this. How to write this Boolean expression for this? AS BS ZS bar plus AS bar BS bar ZS, right? Can I write like this? Yes or no? Sorry, here AS bar BS bar into ZS bar. So, this is a Boolean expression. With this respect, several times I have seen a GATE paper. Several times I have given. Suppose is given a question like this. There was a question 2017 paper. A and B are C. There are three numbers are there. A plus B added stored in C. A is a 8-bit number, B also 8-bit number, C also 8-bit number. Now said same thing. A means 8-bit number 0 to 7. A7, B7, C7 are the sign bits. Now one of the option would be like this. One of the option is there like this. This is only there like this. A7, B7, C7 bar. A7 bar, B7 for C7 will be there like this, one of the option. You can select it. Right, second condition. What second condition said? What is second condition? sign in and sign out. So like if you take it, like suppose A in, A out, like a sign in and sign out is there, sign, carry in, carry out is there, right? Okay. Now understand, to check the overflow condition, okay, what is said? If carry in, carry out both are not same, carry in, carry out are both are not same. Yes, this is directly asked in GATE, sir. Yes, exactly I am trying to say. Exactly I am trying to say this only. So I am just repeating. These are two conditions I mentioned here. So from, yes, 2017 for 2 mark question asked. For 2 mark question asked. See, under arithmetic operations, you no need to worry, like no, they given two numbers, add it, what is the result? They won't ask this way. Very simply, for under signed case, signed number case, when two signs are added, so how to check the overflow condition? Otherwise, they will see, give numbers also, they give, they ask to. Option they will give, what condition used to check. There are two conditions which I mentioned. Numbers are of the same sign, the result is opposite sign, then result is overflow. Carry in bit is not, so carry in bit to sign position and carry out sign position are not same, then also there is overflow. This condition also we can test it. With this condition also we can test the overflow condition. Which notation under? Which notation? Sign, one sign, two's complement case, ma'am. In case of sign magnitude, I mentioned na, sign out, so carry out bit is a under sign position, indicate the overflow. Like this, I shown the example also for this, like this. So this carry out we got here. So this indicates the overflow. Fine. So let us see for this example also. For this example, we'll see. Example, if I see, okay, minus 80 plus minus 70, if I want to add it. So this is 150 only, right? Now 8-bit register, 8-bit register. Tell me all of you, in one's complement, what is the range? Minus 127 to plus 127, right? One's complement. Two's complement is minus 128 to plus 127. Either it is a one's or two's complement, you cannot store this number. Yes or no? Then how we can do? First to write down. Example, if I ask you to write the like two's complement representation for minus 180, minus 80. How to write minus 80 in two's complement? How to write the minus 80 in two's complement? As I mentioned clearly. So write the powers. 2 power 0, 1, 2, 4, 8, 16, 32, 64, 128. So 120 greater than the 80 or not? So if I plotted this position, what you will get? Minus 128 you will get. Something positive value you have to add it to get the 80. How much you have to add it? So 48, is it 48 only? 48. How to get the 48? 32 plus 16 only? Yes or no? The 48. This remaining portions are 0 only. Yes, Shiv. Like tell me this, is it correct representation of a 2's complement of minus 80 or not? Similarly, minus 70. How to write? So 128 position, 1 I have take, 128 minus 70, how much? That will be 30 plus 58. Is it 58 only? So now, so this position is 0. I have to take this value, right? Yes or no? So this one, then I will take 8 and 10. This is a 0, right? Yes, sir. So 8 plus 2 is 10. This gives how much? 48 plus 10, 58. So 58 if you remove, remove the 58 from 128, you will get a 70. Now perform the addition. 0 plus 0, 0, 0 plus 1, 1, 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0, 1 carry. So 1 plus 1 plus 1, 3, 1, 1, 1 sum, 1 carry, 0 plus 1, 1, right? Now say 1 plus 1, 0, this is 1. So this is a result. So I perform the 2's complement addition. 2's complement addition I perform, right? 2's complement addition I perform, right? One important point you have to notice. When you are perform the addition by using the 2's complement notation, if you get a carry, you can ignore. This ignore, first ignore it, ignore. Then you see, these are the two sign numbers, right? What is sign? 1, 1 is same sign. What is the result? Opposite sign. So is overflow or not? Yes, overflow. Signs are same, result is opposite, overflow. This way you can test it. This way you can test it. Other way you understand. So 0 plus 1, 0, 0 plus 1, 1, What is a carry in? Carry in 0. Carry in 0, right? 1 plus 1 how much? 0, 1. Carry out. So now both are not same. Here sign in, I will take sign, carry in value is 0, carry out value is 1. See, 0 plus 1 is 0, sum is 0, carry out is 0, right? Carry out is 0, right? For this carry in, right? This is carry in. 1 plus 1, 0 is a sum, carry out is 1. 0 is a carry into this one. Both are not same. That is also indicate overflow. This we can test it. This is all about, under arithmetic operations. So quickly we can move to next one. Memory part will observe. Memory organization. Because floating point arithmetic, there was no questions also, but major you focus on arithmetic operations like signed part only. Signed part need to be focused. Now look at the memory organization. So in the memory organization, what are the things we are going to understand? First area, memory hierarchy. Memory hierarchy. The second, we will see the main memory. The third area will observe on cache memory. The fourth aspect we'll see the main memory over cache or secondary memory part will observe. Secondary memory part we will observe. So these are the four aspects. So we'll discuss under memory organization. So first look at the memory hierarchy. Okay, because in the gate point of view, if I say, so among these four areas, this is the area we can expect the question. I'm making the star. And the compulsory question will be there here, like compulsory cache. I'm making the 4 stars. You can expect the question from cache memory, especially cache address mapping would be there, or cache updation method. So combiningly they can put a question. And secondary memory, especially on disk part, nothing but cylinder type questions they can frame here. And in a main memory also like sometime RAM configuration, RAM chip based questions also we can expect. All 4 areas are important. All these 4 areas are very, very important from memory. So together, see, if suppose case will be the question is framed from cache, and we may expect from here or may not be expected from here. Example, see, either if the memory hierarchy question is framed, so we may not get from the cache memory. Like this, you understand. So together I can say from this area only I can tell, like we can get 1 to 3 marks here. Either 1 mark question or 2 mark question 1 and 1 mark question. So simply otherwise I can take 2 to 3 marks possible. Here is 1 to 2 marks possible. 2 marks only, like minimum 1 marks we never seen. 2 marks we can expect here. 2 marks we can expect. From secondary memory itself, if the question is framed, 2 marks will be there. Fine. So let us look into the memory hierarchy. So I hope you studied of the memory hierarchy. What memory hierarchy is talking about? So memory hierarchy, please to understand, in a computer system, various memory components are there, like primary memories and secondary memories. Like primary memory component, if I talk about cache memory and main memory, right? Secondary memories in terms of hard disk is the magnet tape is there, like this. Various memory components are there. Fine. Memory hierarchy is talking about arrangement of these various memory components so that average access time will reduce. That is the ultimate objective of the memory hierarchy. Arrangement of this memory various memories is nothing but memory hierarchy. We are arranging. What is the purpose to arrange? Purpose is to arranging what? To improve the memory operation. Nothing but average memory access time going to be reduces. Getting my point, all of you? Because some memories are slower memories, some memories are faster memories, right? So like secondary memories are slower, main memories are faster. But putting all together, you have to use it. And CPU, if you see, CPU is very fast rate, this memory is very small. So now you have to know, we have to make it like this. Ye balance you have to make it. We have to make the balance between the processor and memory component. That is the reason this all the memory components are, we are arranging in some order to speed up the memory operations. So hierarchy form, if you see, the top level of the memory hierarchy plays what? Cache memory. And the main memory occupies a central position of the memory systems, main memory. So main memory can be directly accessed to the processor or indirectly can also access like through cache memory. It can be directly accessed. And secondary memories are the lower memories in the memory hierarchy, which is not directly accessed by the processor. So processor required some I/O interface to access it. Fine. So this is hierarchy form, understand. What is the ultimate agenda for arranging these memories? To reduce the average access time, not individual access time, average access time we are reducing. Like how we can understand? So one example I would like to say, so in the memory hierarchy, at home we have a refrigerator, right, to store the vegetables, right, frequently used vegetables we store in the refrigerator. So that may reduce our time, like you understand, like 1 week, what are the 1 week so required the quantity of this vegetables, we can keep it. So if anything is not there, the nearest market would be there, nearest market you can go. If that market also not there, you can go to so big market. You understand, processor, so initially it will try to search in cache memory. If they are present, it's fine, it given to the processor, it will take very less time. And if it is not the available cache memory, it will search in the main memory. If it is present, given to the processor by storing in a cache memory. If it is not there in the main memory, it will go to search in secondary memory. Then take the bulk data from secondary memory, place into some main memory, some place into cache memory, remaining given to the processor. Like you understand, from big market, that material, the vegetable comes into nearest to small market. From that small market, something you are fetching into home, refrigerator, right? So all the time your mother, when you cook any dish, she'll try to find out in what the cache memory. Cache is nothing but refrigerator. If something is not available, then only you ask you to go, so get the things in nearest market, right? So that way you understand here. So processor directly, so processor, please understand, a processor point of view, it has to go to main memory only, but we are going to search into cache, then main memory. If it is not, then we will go to second memory. So ultimately we want to reduce what? Average access time. Fine. So how this memory hierarchy is connected? How this connected? So means to understand. So before this connection, what I want to show you, the performance of this memory hierarchy, performance of the memory hierarchy given by the based on what? IT ratio. Please understand, IT ratio. IT ratio. What is the IT ratio? What is IT ratio? Performance of the hierarchy given by the IT ratio. So number of hits to the higher level memory to the total number of references. Means to understand, during some period of time, so n1 operations, n1 number of references I given, so got it out of please n1 plus n2. So total reference are n1 plus n2. Total reference means what you understand simply, processor issues some reference to fetch a data or instruction from the memory. The memory could be cache or main memory, secondary memory, it won't bother. Ultimately I needed data. So these are the total number of references given by the processor, out of which only n1 are present in where? Top level memory. That we call it. That we call it. So number of it to the total number of reference given by IT ratio. Understand, if IT ratio is more on top level memory system, overall performance of the system also better. If IT ratio of the top level memory is less, overall memory performance will be less, because it is increase the time. So that we have to observe. Now this memory hierarchy, how we are going to arrange it? The memory hierarchy, how we can go into arrange? Case number 1, parallel connection. Case number 1, parallel connection. Please do understand, all of you. Various memory components are present and all the components are directly connected to the processor. Getting my point? So this is L1, ma'am. Please understand, L1 memory. I am writing L1 memory. This is let me use other color. It may not be visible. This is L1 memory. This is L2 memory. This is CPU. This is CPU. Getting my point? CPU. Understand? This connection of the like memory hierarchy can be done in 2 ways. One is a level by level connection. Second is a parallel connection. Look at the parallel connection. Parallel connection, nothing but to understand, all various memory components are directly connected to the processor, having the separate buses. each memory component having the same, like its own separate bus will be there. It is implementation cost is more, but the faster mechanism, right? Faster mechanism. This is faster mechanism only. Suppose if I take in the memory hierarchy has only 2-level memory system is there. 2-level memory system is there. Now processor giving some reference. Reference means placing address to fetch an instruction or data from the 2-level memory system. Now I want to know that how much time is required to perform one memory operation with this 2-level system. So that is defined by average access time. So I am writing T average. So when I write T average, nothing but amount of time taken to perform one operation from this 2-level memory system. This operation can be taken from level 1 or level 2. It is whatever it is, but how much time it will take together putting into total 2-level memory system, that is what T average. So operation nothing but it can be read operation, it can be write operation. CPUs giving address to read a data from 2-level system, or CPU issue the address to write a data over the 2-level system. Either read or write reference, when the movement is given, how much time it will take given by TJ average. Let's take, so accessing the level 1 will be taking T1 time and level 2 is T2 time, assume that. Parallel connection means what? You know, right, already. So processor will place a parallel to address, parallel it will place it. If it is available level 1, it will be ignored. If it is not available, it will continue to search level 2, given to the processor it will go. Am I right or not? Both are parallelly given. So with this concept, with this consideration, what is a expression for the T average that is given by first. So if I take the iterate of this one is H1. So now if H1 is present, if there is L1, so T1 amount of time required, right? If there is a miss, 1 minus H1 we write miss. So we have to go level 2, that is T2. So this is simple expression, the simple expression for getting the average access time in a 2-level memory system which are connected parallelly. This expression you need to use it. So same thing you can extend it for 3-level also. 3-level means what, how it will happen? H1 into T1 plus, if there is a miss in 1 minus H1 into level 2. Level 2 also you have to check whether it is present or not into H2 into T2. If there is a miss in level 1, level 2, then you have to go on like if H1 like 1 minus H1 into 1 minus H2 into level 3 I can write it. So that you can extend for level 3-level system. Fine. This is one case, parallel connection. Next you will see level by level connection. Level by level connection, nothing but to understand. Processor is directly connected to the level 1 and level 2 is connected to level 1 like this. Level 2 is connected to level 1. Getting all of you. So let me take the amount of time taken to read and given to the processor is T1 from level 1. The amount of time taken to read or write a word from level 2 is like take it is T2. Now here a T1, T2, please understand. T1 is from level 1 to CPU. T2 is from level 2 to level 1 only. Because when there is a miss in level 1, we are going to search into level 2. From level 2, we are placing in level 1. That you would understand. From level 2, it is placed in level 1. From there, the word is handed out to the processor. So most of the practical cases, this is being implemented. Because parallel connection is costly. Parallel connection is costlier. Getting my point, all of you? Parallel connection is costlier. That's what we are going what? Level by level connection. We are going for level by level connection. Look at here now. So T average expression, write down. I hope you know, but just recall what is the expression for this one. First I am searching. Suppose if the word is present level 1, that is maintained by H1. If there is a miss in level 1, we are going to search in level 2. Take the word from level 2, placed in level 1. That is handed to the processor, right? So H1 into T1 plus. If there is a miss in level 1, then what to do? So from level 2 to level 1 transfer, level 1 to CPU is given. This is expression, please understand. So this expression for level by level connection. This is expression for level by level connection. I hope you understand. So this further can be simplified. T average. If you mathematically, if you simplify it, that will give one T1 plus 1 minus H1 into T2 will give. So this expression mathematically, if you simplify, this will get. So I'm suggesting either you can use that expression or this expression for when level by level connection is given. So how I can read it this one? So T1 is hit latency. So I'm writing this what it time or it latency of L1. 1 minus H1 is what? Miss rate. Miss rate of L1. What is the T2? T2 is what? It latency latency of L2, or we can call miss penalty of L1. How to read this statement? Look, all of you. So look, go and see here. What I said T1, if there is a it in level 1, so T1 amount of time is required to given to the processor. Suppose 100 times I searched, total CPU given how many references? 100 references given. Out of 100, 80 times it was found in L1 only. It was found in L1 only. So nothing but 80 times, right? 80 times by out of 100 is it only. That's what 80% it here, right? Yes or no? 80 times you have to take T1 only or not? Yes. So remaining 20 times you have taken from where? Level 2. Level 2 means you understand from level 2 to level 1 you transfer given to the processor, right? So 20 times into T2 plus T1, this you have to understand. So for parallel connection, I multiply only T2 only, not T1, because we are level by level connection, right? This T1 is extra. So this mathematical, if I simplify, so the T1 is included here. Should not misunderstand. Both are same only. Previous expression, this is same. How to read? It latency of level 1, miss rate and it latency of level 2. Or so there is a miss in level 1. That is the reason I need to go and access level 2 or not. That's a penalty extra. Are you able to understand this? You have to read like this, no? So level 1 miss occur, because of this miss in a level 1, I am going to level 2. That extra time required, that is we call miss penalty of L1. Miss penalty of L1 also we can say. Getting my point? If there is a miss in level 2, then we have to go to level 3, right? We have to go to level 3. From level 3 how to? From level 3 to level 2, level 2 to level 1 given to the processor. That way you understand. So now if I want to write it, 3 level system. If I want to take 3 level system, level 1, level 2, level 3. Okay. Now I am taking T1, access time T2 and T3. So also I am taking H1, H2, H3. Means what? H1 is a level 1 iteration, this is level 2, then level 3. Level 3 is always 1, right? 100% true. Level 3 is always 100% because level 3 definitely always hit, that is. Now see, if I want to write the expression T average equal to, I'll write simplified expression T1. So it latency of level 1 plus when there is a miss in level 1. So what is required? Penalty, miss penalty required, miss penalty of L1 required, this miss penalty L1 plus. If there is a miss in level 1 as well as miss in level 2, then penalty required, T3 is a penalty. So this you can write T1 plus M1 T2 plus M1 M2 T3 also we can write it. What is M1? M1 is miss rate. Miss rate of L1. What is M2? M2 is miss rate of L2, like this one. What is the T3? Miss penalty of level 2. Miss penalty of so you like now see, this is simplified expression. Actually this is simplified expression. If you include H1 also, that is also fine. You can use it, you can include. But how I am going to read this expression? How I am see, if you if you look at this last one, I will explain that also. I'll give it, no problem. I will explain. Be stay. How simple it is, see, how many are there? 1, 2, 3 only there, right? So T1, M1, T2 plus M1, M2, T3. How simple it is looking like. If instead of writing everywhere H1, H2. What is the meaning? I'll tell you first of all, then I will write it. That also you can write it. So if go and see the diagram, this is the diagram, right? This is every time you have to go and search in level 1 or not, that is compulsion, because you cannot go to level 2. Whether it is present or not present, you cannot go directly level 2. First you have to search in level 1 only. Yes or no? T1 compulsory required. I am writing, see, that's what I written. T1 compulsory required. Whether it is a miss or it, level 1, right? Suppose only it assume that, even level 1 it assume that. This all the things are not required, only T1 is required. If there is a miss, level 1 there is a miss, then you have to go to level 2. That's what I am now. If there is a miss in L1, M1 nothing but if there is a miss in L1, extra penalty required to go level 2. That's what T2 time extra required. When you write extra nothing but T1 included through this one mathematically. When there is a miss in both L1, L2, extra T3 is required. That way you understand. So I can write this expression. So full expression if you want to write it, look this, how full expression will go. So T average equal to, I'll write it. So T1 H1, yes or no? If there is a it in level 1, T1 required. Now I am writing 1 minus H1 into, look this all of you, look this all of you. Then if there is a miss in level 1, there is a miss in level 1, then what to do? I have to check level 2 it or not. If there is a miss in level 1, you cannot guarantee that will present in level 2 or not. Can you guarantee that is present in level 2? Respond. If there is a miss in level 1, can you guarantee that will definitely present in level 2? No. So I have to maintain H2. So if it in level 2, then from level 2 to level 1 you have to transfer, level 1 to CP you have to give it this one. If there is a miss in level 2, then you have to go to level 3, right? This is a miss. Level 3 iterative not required to mention because level 3 always it only. So level 3 to level 2 you have to transfer, level 3 to level 1, from that you have to give to CPU. This is the expression. Yes, is it correct now? This is a complete expression. This is complete expression. This only directly I rewritten. Mathematically, if you simplify, you will get this only T1 compulsion, 1 minus H1 nothing but when there is a miss in level 1, so extra T2 required, level 2 required. If there is a miss in L1 as well as L2, L1, L2, then T3 is required. Both are same, go on, you can simplify. Both are same equations. Both are same only. See, it is, that's what I said you. This is compulsion for checking. Then if miss occur, extra T2 required. If there is a miss occur, extra T3 required. The T1 is included all the way. Okay. So now, so which one is simple? Simple to understand. Is it this one or not? This one is simple or not? So many parameters are not involved. So simple to understand like this. Hit, there is a miss in L1, extra penalty required L2. If miss in L2, extra penalty required L3. That's all. So terms you have to understand simply term. What is the T1? Hit latency of L1. What is M1? Miss rate of L1. What is the T2? Miss penalty of L2. Miss penalty of L1. Sorry, miss penalty of L1. Penalty I am writing, miss one. Miss rate occur in level 1, penalty required. What is M1? Miss rate of L1. M2? Miss rate of L2. T3 is what? Miss penalty of level 2. Like this you understand. So this is the expression under level by level connection. Suppose some more thing I want to show here. So case number, the exploiting the spatial locality. Exploiting the spatial locality means what? Generally cache memory maintain two things. One is temporal locality, one is spatial locality. Spatial locality means what? If there is a miss in level 1, then obviously go to level 2. So what that word is transferred to level 1. What we are trying to say, we call read allocate, write allocate policy we say. We'll explain later. So when you go to level 2 to get the data, don't take one word. So adjacent group of words you transfer, so that it will reduce the future penalty. If there is a miss in level 2, go to level 3, take some more blocks of data that you transfer to level 2. From there you transfer to some blocks, words. One word is given to the processor. If you do so, what happens? In the future, so next time when CPU is referred, that may be present in the highest level. To reduce this future penalty, what we are seeing, so look this. So I am taking, so T1 is a level 1 access time, assume that. Now this hit rate is H1, assume that H1. There is a miss in level 1, I have to go to level 2, right? Level 2. So instead of fetching only one word, I am transferring the two-word block. Please understand, two-word block I am transferring. So generally is a two-word. So T2 into two-word. If there is a miss in level 2, what I will do, I will take like this, four-word block I am transferring here. So from there a two-word is given, from there one word is given. So understand now, T3 is access time and 4 words I am multiplying. So this is the third case, spatial locality. Yes. So did you understand this point? Did you understand? With this respect, can you write the expression? Can you write the expression T1 plus 1 minus H1 into T2? I should not write T2. I will write TB1, block of ones, plus if there is a miss in level 2 also, 1 minus H1, 1 minus H2 into I will write TB2, I will write it. What is the TB1 here? TB1 nothing but 2 times of T2. TB2 is what? 4 times of T3. Why, sir? Because T1 and T2 access time is what? One word access time. You are transferring 2 word, 2 I multiply. You are transferring 4 word, 4 I multiply. So this is expression for that, ma'am. Got it, this one? So this will please note of it carefully. This this basically cache address if you see updating methods we have. In that case, question can ask in this way. In this manner, question can be framed. Block of words are transferred. Or in the memory hierarchy also can frame a question like this based on this data. So 3 cases I mentioned. One is parallel connection, second one level by connection, third case is a level by level with spatial locality. So with the various expressions already given. So I hope you understand. Note of it. Yeah. So shall we move to other topic next? Is it fine now? Okay. So next one. So this is all about cache memory. Let's look into main memory part. So that we discussed memory hierarchy, right? So let us focus on main memory. The previously we focused on, so under memory organization, first aspect memory hierarchy, then main memory, then cache, then we will go to secondary memories. Under main memory, there are 2 things we need to understand here. Okay. What are the main memory components? RAM RAM is there, ROM ROM is there, right? This RAM is what read write memory also we can call. We call what read and write memory. Read and write memory it is. Read and write memory. This is what? Read only memory. It is a read only memory, please understand. So read only memory. Read only memory. This read write memory classified into 2 things. One is SRAM. Second is the DRAM. I hope you understand. These SRAMs are nothing but used for constructing the cache memories. Getting my point? SRAMs are used to construct the cache memories. DRAMs are used to construct your main memory. The system containing main memory, right? RAM you call, that's DRAMs only will be there. This DRAMs are, in a DRAMs, data is stored, binary information stored in terms of capacitors. Capacitors. In a SRAM, data, binary information stored in terms of flip-flops. You know the differentiation, right? Flip-flops. That is the reason SRAMs are costlier. SRAMs are costlier than the DRAMs. That's what cache memory, if you see, cache memories are costlier, which are smaller in size, like in terms of MBs, 4 MB, 8 MB, 256 MB, like level by level cache, if you see, also in terms of MBs we see. So when it goes to our main memory in terms of GB, we have a RAMs like main memories, 2 GB, 4 GB, 8 GB, 16 GB RAMs are there. So which information stores in a what? Charges in a capacitor form. You know capacitor nature having the leakage problem. Yes, capacitor leakage problem. That's what periodically you have to refresh it. Periodically we need to refresh to keep the same information in case of RAM, DRAMs. And why DRAMs are chosen means it has more density actually. Power consumption is less. That is the reason they are used for storing the main memories. Our main memories in a computer system are DRAMs only. And flip-flops nature, 1 bit, 0 or 1, this is costlier to implement. That is the reason only cache memories are limited to that one. So now our focus. So when it goes for ROM, read-only memories, or simple ROM will be there. Have some classification, right? PROMs and EPROM. So double EPROMs are there. Sir, what is the purpose of the ROM? Somebody could tell. What is the purpose of the ROM? The purpose of ROMs, to please understand, to load the bootable programs. Bootable programs. Right? Bootloaders are there. Essentially it is contain the bootstrap programs. So which is required to load the operating system from secondary memory to main memory. And also it can be used for storing the control words. So control signals are represented by control words. The control words are stored in control memory. The control memory nothing but ROM only, read only memory only. So it has like classifications like simple things. So let us focus on this DRAMs only. The RAM nothing but our main memory. Main memory, how physically we can see. So look at the RAM chip configuration. This is the RAM. If I take the memory size 128 by 8, please understand, if I take the memory size 128 by 8, what this indication? There is a 128 lines or 128 words, please understand. 128 words are bytes. Bytes are there, or locations also we can tell. Locations also we can tell. Locations. This is 8 is nothing but word length here. Word length or location size. Location size, location size, please understand. So 128 by 8 nothing but, if I take the 128 by 8 dimension of the RAM chip, if I take, so 128 words or 128 location, each size is 8 bit like this. So which is associated with CS1, CS2, read and write and address 7 bits are there, and this is data. So any memory if you take, this RAM is associated with 3 things. One is we perform the operation, read and write operation, we perform it, right? To perform read and write, I need address pins will be there, and the control pins will be there. Control pins defines what type of operation you perform, read or write. And data, what is the data? Transferring the data, this data. So data bus is the bidirectional, address bus is the unidirectional, right? So now controls nothing but you understand, either read or write operation. Now I mentioned CS1 and CS2 bar is there. So here CS1 is there and CS2 bar is there. Do you know differentiation? What is the CS? CS is chip select. Do you know differentiation? CS1 and CS2. CS1 and CS2. Understand? The modern RAMs, if you see, the memory also divided into some modules are there. Means the memory is also organized in terms of smaller size chips. When we have multiple chips, to select the one chip, the CS1 being used. Chip selection, enabling the chip, CS1. The CS2 is a complement, like it is 0, that is 1 complement will be 0 like this. If it is 1 complement or 0. So what is this opposite here? ROM memory is the read-only memory. Most of the time what happens here, chip, if you take any chip, some portion is the RAM space will be there, some portion the ROM portion will be there. If you take RAM chip is there, right? In the RAM chip, some portion is allocated for the RAM data, and other portion is allocated for ROM. Now suppose if you want to perform read or write operation over the chip, now you have to distinguish this read or write operation is carried out from the RAM or ROM portion. So this will be what? Distinguish. Getting my point, all of you? So when it is 1, what does mean? You cannot perform the operation in ROM. When this is 0, then you are performing from the ROM portion. So that's what these pins are there. These 2 pins are there. And anyway, read write signal will be address 7 bits are. Why address 7 bits are? 128 locations are there. To identify one location, to address one word, 7 bit is required. 7 bit is required. Sir, from this area, what type of question we can expect, sir? The question they'll ask, see, simple. So they want to expand the memory. They want to expand the memory by using the smaller RAM chips here. They will ask question, how many chips required to configure this memory? Suppose I want to configure, getting my point, I want to configure, otherwise you want to configure. Example, practical cases if you see, initially when you purchase the computer system having support 2 GB RAM only there. So right now you want to configure to, you want to expand the memory into 8 GB. What you can do? There are two options for you to expand the memory. One is simply remove that slot 2 GB RAM. So by 8 GB RAM directly you can insert. So total memory size is going to be 8 GB. The other approach is that take 4 2 GB RAM chips you can insert in a slot. So 4 RAM chips you insert. Then what happens totally? It will become 8 GB or not? So question we can expect in this area. I want to expand this amount of memory. Then how many chips required to address them? So like how many chips required to configure them? So this kind of question they can expect. So for this answer, what you can do? Number of chips equal to total memory size by basic size. You want to divide it. That's what now. Organization larger size capacity of memory with lower small chips, smaller denominations. You understand? This what expanding of a memory by using the smaller one. Example, one question I'll take it. Construct 1024 byte memory by using the basic RAM chip of 256 by 8. Calculate the total number of RAM chips required and size of the decoder required to address them. So now number of chips equal to total memory size almost 1024 bytes. 1 byte equal to 8 bit. Can I write it or not? Yes or no? Divided by basic size almost 256 by 8 is there. Now how much it will be? 4 or not? So 4 chips required for them. Okay, 4 chips required. So second question, decoder size we need to find out. Decoder size. So look this all of you, decoder size. This 4 chips if I place in vertically, so I have to enable one of them, right? 4 lines required, right? So that you understand 2 by 4 is a decoder required. 2 by 4 decoder is required. Like that you can answer it. So couple of problems you practice on this area, you can able to answer it. There was a question 2013 paper, 2 mark they have framed on this area. You go and see. They given some 16K by 1K word memory, 1K. So now 16K by 16 bit memory and the basic RAM chip is 1K by 8 memory is there. Then to construct this memory size, how many? What is size of the decoder? Like they ask how many 2 by 4 decoders required? This kind of question you practice it. So you are in a position to answer this kind of questions now. Yes, this type of questions only we can expect from this area, not other things. So this main memory part is over. So now next let's move on to the cache memory. Here we need to spend the good amount of time under cache memory. So we need to spend the good amount of time. Fine. So let's have a small break of 10 minutes. Then we'll continue this part now. Now let's move on to the next topic, the cache memory. So in the cache memory, first of all, we will understand the importance of the cache memory. Then we'll see the cache memory design part. So design parts, what are the basic elements required for a design in the cache memory, that we'll observe. Because for the gate point of view, please understand, definitely we can expect a question from here. That is 2-mark question. That is easily solvable question, ma. Please observe. So first of all, you tell me what is a cache memory. As I mentioned, cache memory is nothing but SRAM only. The physically, if I talk about the cache memory, nothing but what? SRAM only. So what is the purpose of cache memory? Yeah, please understand. The cache memory is to reduces, it will reduce. If I keep the cache memory, it reduces the average access time. How it will reduce, sir? You understand, a program contains the many instructions which are repeatedly executed by the processor. The data or instruction which are repeatedly executed processor, that if we keep into this high speed small component, small memory component, then what happened? Total average access time going to be reduces. That is the reason, you understand, processor chip only. Most of the architecture in a processor chip only cache memory is there. In the modern system, if you consider, cache memory itself having the many levels, level 1, level 2, level 3. Obviously, level 1 cache memory is part of the processor only. So what we are keeping? Simple thing, everything you will keep only. From the data will, for each data will move from main memory to cache memory, it will move. So what is existed in the cache memory? Nothing but the instruction data which are repeatedly accessed by the processor, which will stay in cache memory only. If it is accessed by only one, so other data comes and replace it. So ultimate objective of the cache memory to have what? Frequently accessed data. If you keep it, then overall average access time reduces. So that's the point you have to understand. So I can draw CPU is there, like the CPU, you understand, this is CPU and the main memory, this is a main memory. So symbolically I am showing, it is a between main memory and processor. Symbolically I can say it is a between processor and main memory. But physical structure, physically if you see, cache memory is part of the processor only. In the modern architecture, it has many levels. Some levels will be outside the chip, some levels will be inside the chip only. So that you would understand. So what is the object? I said to reduce the average access time, we are keeping cache memory which contain the frequently accessed data. Frequently accessed data. So this cache memory maintains the two things, it maintains the locality of reference. Theoretical question they can ask, So statement, choose the statement, or match the statement question, you can see. Like some other memories also has some property would be there. Example, if I talk about associative memory is there. Associative memory, content addressable, that's not, we don't have address. In associative memory, we don't have address. Based on the content only we can access. That property is what? Content addressable memory. Cache memory containing what? Maintains what? Locality of reference. What does mean the locality of reference here? You know, right? All of you. Locality of reference, nothing but understand. Locality is some portion of the memory. So that portion of the memory is frequently accessed by the processor. And the remaining part of the memory may not be accessed by the processor many times, maybe one time, even not even single time also. So the area where processor is accessed several times, that area we call as a locality of reference. So what are the areas are? Please understand, loops, right? Loop. Example, if I take for loop, the instruction which is specified in a for loop repeatedly will access or not, that we called as a locality of reference. Or you understand there is a procedure or function which you define that is calling many times, So function could be, data structure could be, loops could be considered to be as a locality of reference. Getting my point? This locality of reference also manifest into two things. One is temporal locality. Second one is spatial locality. Differentiation, spatial locality we already have seen. Spatial locality nothing but the moment you access something from main memory. So one word you are issuing, you are going to access the data from main memory. So along with that access data, some group of adjacent data, if you take it and place into cache memory, what happens? In the future, processor may fetch the adjacent data. That time, it will reduce the memory access time. It will reduce as a future penalty. So what is the adjacent data? Example, array you are going to access. Array elements are there. So one the one element if access, definitely we can expect the processor may access the second consecutive element also. Yes or no? So that we understand. Wherever data you understand, like no simple thing like consecutive data, if you keep it, if processor refer to that location, definitely it's going to be reduces. That is spatial locality. Temporal locality nothing but same item it is repeatedly accessing. The same item repeatedly accessed processor are likely to be referred in the near future also. So one item if you place in the cache memory, that item may be likely to referred by the processor in the near future also. That's what one item. It is talking one item. Spatial locality nothing but group of items along with the referred data. That should understand. So now let us look into the basic elements for cache memory design. So let us understand the basic element for a design the cache memory. First of all, memory organization we need to do. Then address mapping techniques are there, and block replacement algorithms also there. Cache updation techniques also there. Cache updation technique. So what this is talking about elements like designing of this memory like cache memory. Please understand. If you look at the memory hierarchy, all of you. If you look at the memory hierarchy. So like no, we mentioned like this, right? Here is a cache memory, here is a cache memory, and here is a main memory, here is a disk, right? Okay. From disk to memory, data is transmitted. The data or programs are moved from disk to memory in terms of segment. We call segment, or also you can call pages. In the pages form, it will move. Who is transferring data from disk to memory? Operating system will take care. Am I right? Am I right? Please respond. So data will transfer from disk to main memory by the operating system with help of DMA. Look this on. From main memory to cache memory, data will move in terms of blocks. So who will transfer this data from main memory to cache memory? Done by the cache controller, that we call hardware component only. Hardware only will transfer from memory to cache memory, main memory to cache memory. Now design the cache memory nothing but, so data has to move from a main memory to cache memory, right? Yes or no? Main memory to cache memory has to move it. Now what are the methods are there to map from main memory address to cache address? Then how this cache control functionality will be there? All the things we need to address. That's what. First initially memory organization of the cache memory, organization of cache main memory. And address mapping techniques, please understand, our address mapping technique convert the physical address, that main memory address, into cache memory. Address mapping techniques will convert the physical address, that is nothing main memory address, into cache memory address. We have three approaches are there. So what are the approaches? Tell me. Yes, tell me. What are the address conversion methods from main memory to cache memory? Can you tell me? Sasmal. Yes. Can you give the list? What are those? We are mapping from main memory to cache memory. So one is direct address mapping. Yes or no? Second one is associative address mapping. Third one is what? Set associative address mapping. So which are three are essential, which are important. If the question is framed from the cache memory, so highest, like understand, high priority topic is what? These three: direct address mapping, associative, set associative. From these three, one of the mapping can be asked. Most of the time it is repeated. So what is the purpose of this one? I said have to move the data from main memory to cache memory in terms of block. Who is doing this over? Hardware. These are the mapping mechanisms are there. And during this mapping mechanism, we need block replacement algorithms also. What are the block replacement algorithms are there? You might have studied before. First in, first out. Second was optimal, and third one is what? LRU, least recently used. This block replacement algorithm is also known to, we can say, page replacement algorithm. Both are same only. Page replacement algorithm we use in operating system. Yes, I hope you studied from operating system. There also in frames like pages of the secondary memory will come to main memory, right? We are replacing, right? We use this method, same strategy we use it. So whether if you studied from operating system, that is absolutely fine. Other way you understand, you can go and see these three important areas. FIFO, optimal, LRO. If the question is framed from computer organization, it will mention the block. If the question is framed from OS point of view, they will mention the page. Meaning is same. Page or block is same, but the context is different. CO point of view, OS point of view. Now, another thing is another thing is required, cache updating techniques. We'll observe one by one. First of all, if you see the first one is a memory organization, right? Memory organization. What does mean memory organization? Cache memory and main memory. Please understand, both we need to organize them into block wise. Block wise. Are you able to understand? Memory organization means cache memory and main memory, you have to organize them into block wise. What you have to do, sir? Simply entire cache memory you take, main memory you take, divide them equal size blocks. Divide them into equal size blocks. Block of a main memory is moving into cache memory block. That's what mapping we done. Getting all of you? Organization nothing but arranging the cache memory and main memory in terms of block wise only. I hope you know that how to arrange. You want any example for that? Do you want any example for that, or you know this one? Respond, Sasmal, Amlan, Sasmal. Do you want example for this, or you understood? Simple statement I given. So cache memory, suppose whatever size is there, memory size is there. So both you have to organize them in terms of block wise only. Means you have to divide them by block wise. That's what organization of the memory. Second thing. The second thing is what? Second element is what? Address. Address mapping techniques. Address mapping techniques or address mapping methods. Okay. So what is the purpose of this address mapping methods? I am writing. Purpose is to converts physical address into cache address. Cache memory. That's meaning is what? Mapping the main memory blocks. So blocks into cache memory blocks. I hope you understand. Okay. This address mapping techniques convert the physical address into cache memory, that is mapping of main memory blocks into cache memory. So for that, main memory also you need to organize in terms of blocks, cache memory also need to be organized in terms of blocks only. So you have to map it. What are the mapping techniques we have? One is direct address mapping. Second one is full associative, also known to be simply associative. You can write simply associative address mapping. And the third one is a set associative mapping. So there are three approaches we have. So let us see one by one. Very important important points only we will note out. So look this all of you. So you understand, here is a cache memory. So here is the main memory. Please understand. Here is the main memory. What I said you have to organize them into block wise. Like this, you understand. So this cache memory also you have to organize them into block wise. Getting my point? It is a cache memory. It is what? Main memory. Please understand. Now see. Suppose if I take block size, suppose 16 word are there. What is size of the block I am taking? 16 words are there. This block size also will be 16 words should be there. This also 16 words. Both the memories should be partitioned to equal sized blocks. So these blocks you have to map here. Like getting my, these blocks you have to map like this. You have to map it. Take block, place it. Sir, if I take in suppose example here 0, 1, 2, 3 like this. Suppose 31 blocks are there. Total 32 are there. Assume that. Here if I take there are number of blocks. If I take 4 blocks are there. Assume that 4. Now there are 32. Like any block you take it, place it. So where to place, sir? I am taking one block, I have to place in cache. Where to place? There are 4 blocks, where to place? That's what address mapping schemes are there. So what is the first address mapping? Direct address mapping, full associative or set associative or associative or set. There are 3 are there based on if you see. So generally what happens here, processor, who is the real link processor, some program, your program suppose PI is running in a CPU. To fetch instruction or data, it will generate the address. This address we call logical address from OS point of view. Yes or no? You might have no. Processor generate the address known as logical address. This logical address generated to fetch a data into main memory, not in the cache memory. One more important point. Processor not aware of the existence of the cache memory, simply always giving the address to the main memory only. Processor already always giving the address to the main memory only. Now see, please understand, this logical address need to be converted into physical address with help of, studied memory management unit. Some hardware component I am using and translating it logical to physical address. So now look, the physical address I am taking, I am going to search into main memory. Like we have to go and search into main memory. Getting all of it. Take this physical address, go to main memory, search, get the data given to the processor. But because processor essentially generate the address to main memory only. But we kept the cache memory. Why we kept? To reduce this time, right? Time. So what we'll do, we'll take middle this address. Which address? Physical address. Take this physical address, search into cache memory first of all. Search into cache memory. If it is presented, take the data given to the processor. If there is a miss here, suppose if we miss occur, please understand what to do. Take this physical address, go to main memory. That block you map. First you place here. Here. Then the concerned word is given to the processor. I hope you understand the process. So generally processor not given address to the main memory. It is given not given address to cache memory. It is given to address to main memory only. So middle I am capturing cache control that hardware. If capturing this address, trying to search into cache memory, it is presented given to the processor. If the referred data is not present, then the same address you have to go to main memory, take the concerned block, place into cache memory, restart instruction, then you can search it. This will happen. I hope you understand. So please understand, first method. What is first method? Direct. So what happens under direct address mapping method? We'll see. So mapping method, what is the mapping here? Please understand. So mapping is, we are using the function called k modulo n. I am using k modulo n. This is where k is what? Main memory block number. Main memory block number. Any block. N is the total number of blocks. Number of blocks in cache. I hope you know this one. This is a function we use. So this will give a position in a cache memory, like this one position will give, that place only you have to place it. Correct or not? Yes. Now since memory is partitioned into block wise, now physical address, when the physical address comes from the processor to search a block in cache memory, the physical address, please understand, is divided into 3 parts. Already I am writing. One is a tag information, other is block offset and word offset. 3 things. This word offset depends on the block size. I am writing block size. So the block offset depends on the number of blocks. Number of blocks in a cache memory, if I take n base 2, the value bits, the physical address of x bits are there. So how I am partitioning? Tag, block offset, word offset. Word offset depends on the block size. Block size of 16 words are there, 4 bit required here. This block offset depends on the number of blocks in cache memory. If 4 blocks are there, 2 bits required. And the tag bits, physical address minus this 2 if you do tag bit. Otherwise, this depends on the. So how many blocks are mapping to? Please, how many blocks are mapping to cache memory? This we can do. If I take m by n base 2, I can write it. What is m? M is the number of blocks in main memory. M is what? Number of blocks. Blocks in main memory. That divided by n, number of blocks in cache memory. So that will map to one location, right? Base 2. This way you can get it. Important thing, this is a function, this is address, because question asked this way only. Question asked this, they will ask what is the tag value, what is the like block of, what is the word offset value, they can ask. Now, so this first point, this is second point, right? Third point you see. Let me just a minute more. So third point, understand. Now third point. Here is number of, how many number of comparators required. This question, this is also important thing, comparator. So comparators required in address mapping will be one only. Comparators will be required only one only, that you would understand. And the fourth point to understand here, fourth point is what? Time for it latency. To search something, if you search into cache memory under a direct address mapping, how many, what are the times required? Here time is required, one time for multiplexer were involved, and time for comparators will involve comparator. So this is the whole time required. Comparator will be there, multiplexer will be there, and only one comparator, right? So this only you understand. This is the time for it latency. So these are the important things you can note of it. Mapping function, this is a physical address divided, and this is the number of comparator 1, and it latency will be time for multiplexer for time for comparator. So have you studied, like, no, I hope you studied the mapping mechanism, just we revising with the importance points. These are the important points. Fine. So let us look into the second one. What is second approach? Second approach is full associative address mapping, or simply associative also can tell. Here what to do, there is no any function, no function at all, no function. So what I am placing, you can place any block of the main memory into anywhere in the cache. Simple line, any block of the main memory you can place anywhere in the cache. Now here is a physical address is divided into, this physical address divided into two parts only will be there. One is tag, then is word offset, because block offset would not be there here. Block offset would not be there, please understand. Now please understand, here require more comparators. So number of comparators equal to tell me how many, n will be there. N is number of blocks in cache memory, because any block of main memory you can place anywhere in the cache. Anywhere in the cache, nothing but all the cache block need to be searched. All the cache block need to be searched, ma'am. That is the reason you require more comparators. It is required one comparator, require more comparators. Please understand. Here is, so next point is time for it. Time for it equal to what is there? So all comparators only, time for comparators which run parallelly plus one OR gate we need to keep it. This is a time for it latency. So this second approach. Next. So next is the third one. Third approach. So third one is what? What is third one? Set associative. Set associative. So set associative address mapping. In set associative, what we do? Suppose example, if I use four-way set association, if I use, then what we do? So number of cache block further divided into set wise. So now in this case, mapping function, please understand, mapping function. So mapping will be k modulo s will be there. Here is k modulo s to set, will use it. In that set you can place anywhere. If I use four-way set association, nothing but One set there are 4 block will be there. So mapping will happen to set number. In set you can place anywhere. So that's advantage will be there, right? Where S is a set number ma. Now physical address here divided into, so we have a sets, right? We have a set. So tag bits will be there, tag bits will be there, set offset and word offset will be there. Getting point? So this depends on, we know, block size only. Word offset depends on the block size. Set offset depends on number of sets. Capital is number of sets. The tag will be what? So log of main memory block divided by S base 2. You understand? M is number of blocks in main memory, right? So tag bits we can obtain like this. Now what about other points? So mapping scheme, physical address division. Next one. Time for it. Time for it equal to, we need in this case multiplexers required. Multiplexers plus we need comparators also. We need comparators plus we need OR gate also, because many comparators required, many levels required, so that we need to perform OR operation also. So this is a time for it, you understand. So now tell me number of comparators, how many required in this case? Number of comparators. So number of comparators, please understand, number of comparators required equal to 4-way set association, means 4 required. If I use K, so where is what? K-way set association. K-way set association. If I use a K-way set association, K comparators required. 4-way set association, 4 comparator required. 3-way set association, we don't have 3-way. 2-way set association, 2 comparator. 8-way set association, 8 comparator required, like this to understand. So overall if you observe, the overall thing if you observe here, so 3 mapping mechanisms here, right? So if I take direct, so direct, associative, if I take K-way set association, some different points we can observe here. Look this here. Please understand, it is a slower address. Please understand, slow. Address can be slow it is. It is the fastest one, I can say. Fast. It is the fastest one. It is a moderate, you understand, moderate. Why it is slow, sir? Why it is slow? Nothing but, so please, reason is more conflict penalties will be there. More conflict penalties. Penalty will be there here. More conflict penalty. Here is first point. Second point, no conflict here. No conflict at all. Here is less. That is the reason. Less is a less conflict. So less conflict, nothing but moderate. You understand? Yes. So what we can do, this general discussion, no, end of the session, like I will allocate 15 to 20 minutes. We will discuss definitely. I will address your concern, ma. So you do not worry. Just know you stay sometime. No, let observe what is going on. Let observe, because my intention here. Let's have a quick revision over that. What are the things need to be revised, like line by line, like, because entire book you cannot revise right this moment. So let's have a quick revision over this. Please stay. So definitely, we will address your point. I will address it. Yes. So you should not panic that case. Please understand. I know your pain, but let us give the few points to you. So definitely that will resolve. Look at here. So just comparing the 3 address. Have you studied? Have you revised computer organization? Have you studied the computer organization? Shiv Modi. Great. So just look. These are the things you look. It is slowest address mapping scheme among, I can say. Reason is conflict penalty. Conflict, nothing but, right, meaning of the conflict. Because K modulo and giving some position, every time that will give to some, the position list, though if you have a free space, that we cannot able to utilize in case of cache memory. So you can place anywhere in the cache. It is a faster mechanism, and is moderate, means less conflict will be there. So now the third point I want to write. It is less expensive. Implementation, if you see, less expensive it is, because only one comparator required. It is a more expensive here. More expensive. Why more expensive, sir? More comparator required. It is moderate again. Why moderate side? Comparatively, associate mapping, it requires less comparators here. Because here what I mentioned. So example, fourth point, number of comparators, how many required here? 1. Here how many required? N. Here how many required? P. Getting my point? Comparators. Comparators 1. Here is comparators N. Here is comparators how many? P. If I use P-based set association. Getting my point? The fifth point. So what is the physical address format? Tag bits will be there. Tell me, block offset will be there, word offset will be there. Here is a physical address, only tag and word offset will be there, right? Yes or no? Here, so tag bits will be there, plus set offset bit will be there, word offset will be there. I hope you understand. Differentiation all in one slide. Sixth one, to say it or miss, time for it will be time for multiplexers involved plus time for comparators involved. Here is time for it will be here is a comparators plus OR gate will be there. In this case, time for it equal to time for multiplexers involved, time for comparators involved plus time for OR gate also will involve. Yes. So this is a differentiation we can understand here. It's fine. All three methods are in one slide only, So I hope you're getting my point. So let's move on to the next one. Next thing we will discuss on cache updating technique. So before that, we can see one question. 4-way set associative cache memory unit with a capacity of 16 KB is built using a block size of 8 words. The word length is 32-bit and the size of the physical address is given 4 GB. Number of bits in tag field dash. This question was asked in 2004 as I taken reference to solve like. So now they given physical address not given, but a physical memory given. Physical address space is given how much? 4 GB. But they said here, 4-way set as cache memory with the capacity is given, this size, words are there, the physical address space GBs are there, and is the word length 32-bit is there. You understand? Whenever word is mentioned, word size is given, you understand entire memory in terms of words only. So first of all, you have to convert this memory, physical address memory in terms of words. 4 GB by one word, how much? One word is equal to 32-bit, nothing but how many bytes? 4 bytes only, right? So this gives 1 giga words. This gives us 1 giga words. Do you agree, Shiv Modi and Amlan? Is it correct or not? Please do understand, all of you. Don't take directly 4 GB as a physical memory. Then if you get the physical address for this, it is going to be 32-bit. Now with this respect, what is the physical address going to be happen? Now 30-bit is the physical address. Most of the students confused. So memory size is given 4 GB. Now physical address would be 32-bit. They will take it. Because since he did not mention it directly with a word addressable memory, but he is given block size is 8 words and one word length is 32-bit. So you have to understand it is a word addressable memory. Fine, word. Now physical address we got. Under 4-way set association, physical address 32-bit is divided into how many parts? 3 parts, which I mentioned. Tag, set offset and word offset, right? Like, so set offset, nothing but number of sets I need, right? First of all, number of blocks you find out, number of blocks in cache memory. So if I represent capital N in cache memory equal to, what is size of the cache? 16 KB. What is word length? 8 words are there. 16 KB divided by 8 words are there. Now understand, units are different. Yes. So which one you want? This before one, because this kind of questions they can frame from operating system side and CO side also. Physical address, you may think that this 32-bit. Physical address is not 32-bit, it is a 30 bits only. Reason again I am telling you, You look at using the block size, 8 words are there, 8 words he mentioned, but word length how much? 32-bit given. The size of the physical address space is 4 GB. To solve this problem, I need a physical address. He did not given. The physical address we can obtain through physical memory, that is main memory. Main memory 4 GB is there. First you have to organize in terms of words since word length given. What is word size? 32-bit, nothing but how many bytes? 4 byte. I am divided 4 byte. We'll get 1 giga words will get. 1 giga words will get. So 1 giga 30 or not? 2 power 30, can I write it on this one? Yes or no? So 30 bits of address. Amlan, is it clear? Yeah, okay, look this now. Look this. So in order to solve this one, I need number of blocks. Cache size almost 16 KB by 8 words. So units are not same. You have to convert. Either this part first you express into words, then you divide. Or what I can do, 16 KB divided by. So here only I will change it. One word equal to 4 byte, right? 4 byte. Now, so byte cancel. So this cancel. 2 means 512, right? 512 blocks will get. Yes or no? 512. Yes or no? No, why 512 only? This 2 ja, 2 2 ja. So 1K by half is 512, not 256. That's what calculation you have to do. Otherwise, if you are still confusing what you can do. So this you can express 14 byte by. So 8 into 4, 32, right? 32, 2 power of 5 bytes, right? What is the value it is giving? 9. 2 power of 9, how much? 2 power 9, how much? 512 only? Yes, 512. So what I need now again, so number of sets required, number of sets capital S equal to 512 by, they use 4-way set association. 2 power 9 by 2 power 2, how much? 2 power 7, 128, right? Now you can answer. Word of set depends on the word size, block size. What is block size? Block size is what? 8 words. 8 words, nothing but how many bits required? 3 bits required. Yes or no? Now set of set depends on number of sets. How many number of sets? 128. How many bits required? 7 bits required. Now tag, how many? Tell me how many? How many for a tag? 20 bits or not? So answer for this question is 20 bits. That's possible. That's possible. That's what you have to understand. So you have taken 32-bit as a 8 byte mistake. Oh, that's what. See, Shiv Modi and Amlan, it is again I'm reminding you. Sometime GATE exam, what happens? This is I took the experience of the many students. When the moment if you see known question is there, after reading everything looks to you, everything is clear, you are able to solve it. Yes, you know answer, completely you will solve it, you will get an answer. With this happiness, what happens, we'll read it like that is what, 8 byte is there, 32-bit, you take it a 4 byte, 8 byte you taken. So small division you do, what happens, the other value will get it. Since it is a numerical problem, you will enter some answer. Though it is no negative, but you are going to lose only 2 marks. That's what we should avoid the anxiety. We should avoid the happiness also. We should like one more thing you have to understand, all of you, is a sincere suggestion everybody. Don't make it as any subject your favorite subject during a GATE exam preparation. Every subject treat like a same only. Don't put it more love on any subject. If you put it more love, what happens? You will feel bad. If not able to solve question, you will, suppose any question comes, because this IIT people, they'll make some question wantonly tricky. You is not required to solve all 65 questions, right? To get a higher college also, is not required to solve 65 questions. What is the bother? No need to solve. Some question definitely I am telling you, five questions nobody able to solve in this moment also. Possible, like may solve, may not be solvable. That tricky also there. Ignore it, those questions. But whatever question you able to solve it, read properly first thing. Everything you read properly. Read properly, understand what is intention to ask here. So this kind of mistake can happen, ma'am. Fine. So let's move on to this. This way we can answer it. So let us look into the cache updating method. So why this updation method is required? You might have studied cache coherence problems. Cache coherence problem nothing but same information is presented in different places and differently. What does mean, sir? See, data generally comes from main memory to cache memory, right? From cache memory we given to the processor. Some processor, some update the data. Some it perform the write operation, updated. It is updated only cache memory, assume that. Now, so what happens? That information in a cache memory is different and main memory different. In secondary memory also different. So this all the way data should be same only. Data should be same only. So this problem can be resolved having of the proper updation method. We have a two updation method. One is write through updation. Write through updation. I am writing write through updation. Write through updation. Second one is a write back updation. Write back updation. Write back updation. There are two approaches we have, write through and write back. So these two methods are used in under single core processor. If it is a multi-core processor system, this two method will not work. We have snooping protocol. So snooping protocol used for multi-processor system is more than one CPU is there. So single CPU cases we use write through and write back method. Let's have a differentiation. So under write through method, please understand what happened. Write through method, the cache memory and main memory simultaneously updated. I am writing like this. The moment processor is modified the data, it will write back to the cache and memory simultaneously. It will update simultaneously. Getting my point, all of you? Now, in case of write back approach, every time write operation is performed only cache block. Whenever that cache block is chosen for replacement, please understand. Whenever that cache block chosen for replacement, that moment only it is being updated into main memory. Otherwise, every time in cache only. Getting? Here will be the more updations here. Here will be less updation will be there. Here is only less updation, means every time perform the write operation on cache only. Whenever the block is chosen for replacement, the block you have to protect, means write back into main memory. Sir, how to know that block is written, modified or not? So we maintain for implementation part in a cache controller, we maintain one extra bit called dirty bit we call, or modified bit we call. For each and every block one extra bit is there. If the dirty bit is 0, means you understand the block may not be referred by the processor. If it is referred also, only might be perform the read operations. Any moment dirty bit is 1, at least one word from the block is modified. So that way we can implement it. I hope you understand differentiation. So now, so in terms of updation, like suppose first case if I take write through updation, if I take write through updation take, if I take it here. What I said you, suppose cache memory is there, is a cache memory, here is a main memory, okay, main memory, please understand, cache memory and main memory is there. Here is a CPU, please understand. The moment CPU perform any write operation, it will update here parallel, it will update. Let's say this cache access time is TC, main memory access time is TM. Now I can write T updation time. So T updation time equal to maximum of, tell me maximum of TC comma TM only, right? Yes or no? This will be main memory access time only. Correct or not? Correct or not? Parallel updation. This mechanism performs better when there are less number of updations in application. But some application require to update more numbers, more frequently required to update. Such case it will give the less performance, poor performance. Reason, every time you have to access the main memory, that is suppose taking 100 nanosecond, taking 10 nanosecond, each time 100 nanosecond you have to spend. It can give better performance when there are less number of updations. I hope you understand my point, right? So this is the updation time, Getting all of you, updation time, maximum time only will get it. So now, so do you know that, all of you, how to find the average access time? Do you know expression? under write through and write back mechanism, all of you? Finding the average access time. Suppose CPU given any reference. So to read or write data from this over memories with this write through approach, do you know expression to write? I am asking everybody. Please confirm me. Yes. So let's see here. Let's see. Okay. So T average I am writing. T average nothing but, please understand, if I write T average, amount of time taken to, no, that is in CO part only. So I am taking T average. T average time indicate amount of time taken to read a word or write a word from the memory unit. Either read operation or write operation. So that completely one memory operation required is average access time. T average I am indicating. T average I am indicating. Look, all of you. The CPU is there. Please understand, CPU is there. Here is a cache memory. Here is a cache memory. Here is a main memory. Please understand. Fine now. Fine all of you. Now, CPU can give the reference here, address. This reference, please understand. CPU, whatever the reference is giving, the reference can be, please understand, read operation, yes or no? Read or write operation will be there. Yes or no, all of you? Read or write. When it comes to read operation, it can be instruction read, it can be data read. When it comes to write operation, data write will be there. Am I right or not? This kind of operation will be there. Now see, whatever operation you perform from these memories, we call T average I am taking, amount of time taken to perform one operation. So now, if I use the write through protocol, so it will update into both the case, right? So let's have a expression for this. Look, all of you, I am taking first read operation. First I will take read only. T average read. I want to read the data from cache memory or main memory. Suppose I am taking, so cache memory access time is TC, main memory access time is TM. So now I am taking HR is a iterate, read iterate. What is a read? Iterate. Read iterate I am taking. If there is a it in cache memory, so we require TC time, right? Do you agree, all of you? Just respond. This is correct or not? First I am trying to search read operation cache memory. If it is present, TC time is required. If this read miss occur, so 1 minus read, right? 1 minus read. From where to read? Where to read? Main memory only. So this TC plus TM. TC plus TM. Am I right or not? TC plus TM. Because I level by level connection we considered. When there is a miss in cache, then I am going to read into main memory. But reading means to understand here. So I am two things I would like to use it here. Two things I would look at to use. One is read allocate policy. Read allocate policy. Second one is a write allocate policy. Let us observe. Do you know about this read allocate, write allocate policy? What is a read and write allocate policy? Says when there is a miss in a cache memory, when you either read operation, write operation, when there is a miss in read in a cache memory, we go for main memory. Then, so required word you have to bring, right? Along with the required word, group of words you have to fetch it. That we call read allocate policy. That's what now I said cache memory maintain the spatial locality. So let me write M only, I'll write. This is B, I'll write. B meaning what? Block of words I am bringing here. Block of words are bringing from main memory, placing into cache memory, concerned word given to the processor. So this expression for that. Is it clear, all of you? Is it clear? So whenever read allocate means what? Whenever the read miss occur in cache memory, block of words you bring it. Second case, write allocate policy nothing but when you go for writing into cache memory, so cache miss occur, suppose cache mein nahi hai, then you have to go write in main memory only. Then you write and bring one block of words from main memory. Then I'll ask one question, sir, what does mean write miss in cache memory? What does mean write miss in cache memory? Do you know, what of all of you? What is the meaning of write miss in cache memory? So some words are given to the processor. Let's take x value is there. Some x value 10 is there now. So that x value 10 is there. then 10 is modified to 15. This X value is going to update into cache memory. So now yes, X is not there. How that is possible, sir? Yes, the words are replaced by other block. So in the moment you taken X is given to the processor, it is doing updation. By the time when the other processor came, because cache memory is common for many process, right? Other process we started, that is replace this value. Now when you updated, you are going to update here, that is X is not there, then definitely it is in main memory, right? So then you have to update in main memory. So now write allocate policy nothing but when you go for updating into main memory, bring extra words. That's for write allocate policy. I hope it is clear now. So let me write T average. So write, I am going for write operation. Okay. You know, if I apply the write through protocol, what I am applying it? Write through updation. What is the write through updation saying? That parallel updation. You update here and here. If it is not there, then ultimately you are updating here only, right? So T average, write nothing but simply can I write T updation time, that is maximum of, that only we observed, right? Maximum of TC comma TM nothing but, so it is a TM only. Can I write like TM only? Do you agree with this, all of you? Please respond. You are going to update in cache as well as you are going to update. That is maximum time nothing but TM only. Is it right or wrong? Tell me, respond. TM only. So this is when no write allocate policy being used. This expression is right. When no write allocate policy is used. No write nothing but I am not bringing an extra word from main memory. So if write allocate policy is used, now this T average write operation going to happen. First I am going to write. So that it into update time, update, plus when there is a miss in update, then here update into main memory, plus bring one extra block. Now tell me, all of you, suppose this TB if I remove, this entire expression mathematically will give, this T updation only, T updation only or not? Tell me. If I remove TB, T update into this value into this, if you simplify, you will get only T update value or not? Yes or no? Respond. You will get same only. But what I want to use it? I want to use it write allocate policy. So write allocate policy nothing but when there is a miss, in cache memory, you have to bring one block of words. There was a question in the gate paper. When there is a read or write miss occur, 2-word block you have to fetch from main memory. So the expression is going to like this. 2 expressions I given to you. No allocate policy, if they mention explicitly this point, you have to use this expression. If did not mention, when there is a read or write miss is given, then this you can use it. So now you understand write operation, average write operation, average read operation given. Now reference can contain read and write, both will be there or not? Any reference contain read or write will be there. If I consider both operation will be now T average simple, any reference if I given, whether it could be read or write, how much average time required for a one operation. So that gives percentage of the read operations multiply by T average read plus percentage of the write operations multiply by T average write operations. So this is the final expression it will give. Example, they say in a question, there are 20% operations are read request only. What does mean 20% read? Nothing but 80% is a write will be there. During program execution, processor given this many references. In this references, 20% references are read references. Means 80% references are write references. Each read will go either cache or main memory, right? Average access time. Each write will go cache or main memory, average access time. Putting together this expression. So now with this question, they can also ask throughput. So throughput of the system is given by 1 by T average access time. So this expression also understand. 1 by, what is the throughput, sir? Throughput is nothing but number of words are transferred from memory system to CPU per unit of time. Unit of time is a seconds. 1 second this many words are transferred. So that you can get it 1 by getting the T average access time. Got it? So similarly, let me take the second approach. What is second approach? If I take write back updation, so what is the expressions here? The first one I want to take it T average read. Okay, T average read. Look carefully, all of you. Under write back protocol, same read operation, write operation put in together, both will take it. First I will read it in. Where I will read? So TC into HR. What is HR? Read iterate. When there is a miss in read, where to read ma? From main memory only you have to read it, right? When there is a miss in read, cache memory, you have to read from main memory only. Suppose I am taking the read allocate policy as well as the write allocate policy, both I will consider it. So for read allocate policy saying that when there is a miss in read, you go on read, don't read only one word, you have to read it many words. One block you have to read it. Getting my point? Please observe. So one block of words I read it. I want to place into where? Cache memory. Now cache memory is full. Then what to do? Tell me, please tell me. There is a miss in cache memory. I went to main memory. I bought it. Block of words, one block. I want to place into cache memory. Cache is miss. So cache is full. I don't have any empty block to place it. Then what to do? What to do? Tell me. What to do? What to do? One of the cache block you have to remove or not? Yes or no? You have to remove or not? One of the block you have to remove, right? One of the block you remove. So remove means, please understand here, if suppose any block you chosen for removal. Suppose that block is dirty, then what to do? The block is dirty. Chosen block is dirty. Then dirty means what? That you have to write back or not? You have to write back. Then new block you have to place it or not? Yes or no? All of you. Getting my point? That's what now I want to implement the write updation, nothing but I have to implementation part, what I have to do? Dirty bit I have to keep it. Suppose the one block you chosen for removal, the block is saying that dirty is there. That dirty you cannot remove it. You have to write back into main memory. New block you read it. Such. So I have to maintain that information also. I am writing, when there is a miss here. So I want to fetch a block, right? If suppose X percentage the dirty is there. So because I given a 10 references, 10 times dirty only there. 10 times miss in cache memory. I want to fetch that block. I want to place it in main cache memory. Cache is full. But the one block I chosen for removal, that is a dirty is there. X percent is the dirty. Tell me, if the dirtiness is there, what to do? You have to write back or not? This old block, you have to write it or not? Tell me, you have to write it. Write back into main memory, that amount of time required, one block. Plus, new block, you have to read it or not? New block, you have to read it. Plus, anyway, miss TC value will be there. This is expression. Plus, if there is no dirty, means 1 minus X percentage. So this, if the dirty is not there, selected block is clean, remove, just delete it. Delete only block, new block, you have to read it, plus TC is there. So do you agree this expression? All of you. When there is a read miss, so this will happen. Do you agree or not? All of you. Because there was a question on this like this. If they ask, they can frame it like this. You have to understand. You have to understand the expression. Confirm me, all of you. Did you get this point? Did you get this point? Similarly, I want to write the expression for T average write operation. What is the write operation? Always you have to perform the write on cache memory only, right? Every time you have to write on cache memory only. So, but one time what happened? I just went for writing the cache memory, but the data is not there, miss. So, when there is a miss here, so 1 minus W, miss. Then what to do? What to do? When there is a miss, you have to write in where? Main memory only. I have to write, return. Then write allocate policy I am using, right? Write allocate policy means, then extra words you have to bring. Suppose simply without no write allocate policy is there, simply it is going to be TM. This expression for only TM. When there is no write, because I don't want to bring any extra block. This is expression. But if there is a miss in cache memory, when you go for main memory, write it, bring another block. So such cases, what happens here? Suppose I am considering consider right allocate policy. Right allocate policy, there is a right miss, I want to fetch one block of words from main memory. I bought the block. I want to place in cache memory. Cache is full, then what to do? Tell me. Again, a situation happened. I bought a block, I written my word, that block only I chosen to load into main memory because future it may be refer. Now cache is full, then what to do? One of the cache block you select, then you have to see whether the dirty or not. If it is dirty, X% is dirty, then what to do? You have to write back. So old plus new block, that block you want to choose, plus this TC will be there. If there is no dirty 1 minus X%, then so block TB new plus TC will be there. TC will be there. This expression. Both are looking like the same expressions, but you know, the right percentage different, read percentage different, right? So that you will get a different answer. You will get different answer. So now including this T average equal to percentage of read operations multiply by T average read plus percentage of write operation multiply by T average write. So this expression it will give finally. Yes, yes, all of you ma. Is it clear now? Is it clear? Is it clear? Chalo. So this is the thing. So now this question, if you see, assume that certain processor a read request takes 50 nanoseconds and a cache miss and 5 nanoseconds and cache hit. Suppose while running a program, it was observed that 80% of the processor read requests result in cache hit only. The average read access time they are asking. Average read only. Average read. Suppose, so I am taking TC into there is a hit. If there is a miss occur, then you have to TC plus TM, which we know. But main memory access time are they given? You see. Now see, they said 5 nanosecond and cache hit. What is hit percentage? 80% hit. How much take? 5 nanosecond takes. Plus 20% is a miss, right? Now see, they said 50 nanoseconds on cache miss. So 50 nanoseconds. So please do not add 50 plus 5. Don't add, because they said, you know, a read request take 50 nanoseconds on a cache miss. When there is a cache miss, 50 nanosecond required. You understand, including this value only 50 nanoseconds here. Suppose instead of this way, if the question been asked like cache access time given, main memory access time given, you have to take TC plus TM, you have to take it. But they did not give cache access time. They did not give main memory access time. They said when there is a miss, 50 miss penalty required like this. Miss penalty is a 50. Simplify this one, how much? So 0.8 into 5. The 4 nanoseconds only, plus 0, 0 cancel, 10 nanoseconds, right? So this gives a 40 nanoseconds answer. 40 nanosecond answer. I hope you understand this one. Here, what is the variation here? People confuse TC plus TM, right? 5 plus 55, right? You will get an answer. That is wrong completely. If the 50 nanosecond, if they said for main memory access time, that case 50 plus 5 is the right answer. But they said when there is a miss in cache, 50 required. So that 50 whole time, all the things. Fine, ma. So this is all about, you know, this is all about, you know, cache address mapping. Now, so now we have a cache block replacement algorithm. Please go and revise the, so FIFO algorithm is there, first in first out, optimal algorithm is there, LRU, least recently used. This go and repeat it, because this is common from the operating system. Please understand, this is a common topic from operating system. Only difference would be there, they will mention their page, here they will mention block replacement algorithm. That's the only difference. Let's move on to the next topic, secondary memory. Let's move on to secondary memory topic. In a secondary memory, please understand. So do you study, there are two type of questions they will ask. One is capacity, size of the disk they will ask. Capacity. Second one they will ask IO time. IO time they will ask. So do you know how to find out the size of the disk? Do you know how to find the size of the disk? Size of the disk we can get the number of tracks multiplied by number of sectors per track multiplied by sector size B bytes. Like this, understand. Number of tracks per surface multiplied by number of sectors per track multiply by size of the sector. B bytes is sector. Bytes means, understand this is a B I am taking, B. So in terms of bytes you can say. This will give. IO time includes seek time plus average rotational latency plus data transfer time. Yes or no, all of you? So this is required. Did you study this thing? Amlan and Shiv Modi. Did you study this one? This you remember. Seek time plus average rotation latency plus data transfer time. Data transfer time. So there are these two component is important here. Another thing is important here, like in terms of cylinder question they can ask. So one question I took here like, consider the system with 16 recording surfaces, each surface divided into 1024 tracks, and each track is divided into 250 sector. The sector size 512 bytes. Assume that the disk is rotating 6000 rpm and the average seek time is given as 10 milliseconds. They are asking what is size of the disk here. So size of the disk, please note, size of the disk will be, how many surfaces are there? 16 surfaces. Each surface divided, how many tracks are there? 1024 tracks are there. Each track is divided into 256 sectors. Each sector size almost 512 bytes. So this we can write 2 power of 4 into 2 power of 10 into 2 power of 8 into 2 power of 9. What is the answer this gives? How much it will be? 18, 22. 22 plus 31. 31 means 2 GB. So I studied this in file allocation in operating system. Right. File system. From file system meaning same only, that are. So this gives what? 2 GB. Okay. Similarly, you can find the average seek time will be, you understand, seek time plus average rotational latency plus data transfer time. You find out and substitute, you will get the answer. I am just giving the reference to you. So you can do it, right? Seek time plus average rotational latency plus data transfer. Seek time already given 10 millisecond. Average rotational latency based on this rotation speed you can get it. 6000 rotation per minute. So we need to find 1 minute, 1 rotation time. 1 rotation time, nothing but 1 minute by 6000. That will give almost 10 millisecond. So average rotation of 5 milliseconds you will get it. So data transfer time, again how much you would transfer? 512 KB you need to transfer. So that is need to be find out. So can you able to do it, right? Yes. Chalo, we'll move to other things. Look this. Here another important thing will be there here, cylinder. So now disk is rotation latency. Yes, okay. Please look this. So what I'm trying to say, 6000 RPM rotation per minute is there, right? Rotation per minute. So means 1 minute it will rotate how many times? 6000 times, right? 6000 times. But I need one rotation time required. That is 1 minute by 6000 I can write it, right? So this we can write 60 seconds into 1 second, nothing but 1000 milliseconds I can express, because other component in terms of millisecond I am taking 0, zeros cancelled. This is cancelled, 10 millisecond. Now average rotational latency, what is average rotational latency? Will be 10 milliseconds by 2, right? This is 5 millisecond. Like this, right? Now data transfer rate we need to find out, right? Data transfer rate, DTR, data transfer time. So now 10 milliseconds, please understand, 10 millisecond, 1 rotation, 10 millisecond nothing but 1 rotation time. If I do 1 full rotation, can I be able to track 1 track capacity or not? If I do 1 full rotation, I can able to capture 1 track capacity. So now tell me, 1 track, how many sectors are there? 256 sectors are there. So 10 milliseconds you can read 256 sectors, you can read it, right? Yes or no? But I need only 1 sector. How much time is required? That is only question. How much time required? That gives what? So that gives, so like no, this 256. Now 1 sector time only required, right? 1 into 10 milliseconds. So 256 sectors divided by 256 sector divided by 10 milliseconds. sorry, it will be reverse. It will be reverse. So 10 by 10 milliseconds divided by 256. Now 10 by 256, how much it will give? 10 by 256, very small, 0.0 something it will give. So that value will be there, and average rotation time 5 will be there plus 10. 15 point something you will give the answer. So this will give what? So this value 10 is given already. This value is 5. This is from some fraction will get 15.00 something will get like this. Got it? Got it my point? This. Yes, all of you. Is it got it right? Okay, now see, other important things are cylinder wise, please understand. Cylinder type questions also they can ask. What is cylinder? Nothing but you see, surface as the tracks will be there. Surface as the tracks. This surface also tracks is there. Second floor surface will be there. You understand? Logical collection of the similar position track is indicate the cylinder. You see now, this here is a track like this, like this is a track, this also track, this also track. This is considered one cylinder, cylinder number 0, this cylinder number 1, this cylinder number 2, like this. Cylinder wise they represent the data. So why need to arrange the data in cylinder wise? To improve the data transfer rate. Getting my point? To improve the data transfer rate, if arrange the data into cylinder wise, it will be improved. So in this area, the question they can ask, like there are two address will be there for logical. The sectors will store a cylinder wise, right? For sector address given by two ways. One is you understand, right? Logical address. So cylinder number, surface number and sector number will be there. So another one is a linear address will be there. Linear address will be there. So did you study this thing, all of you? Linear address. Did you study logical address and linear address? This is a logical address. C is the cylinder number, H is the surface number, S is sector number. And second one is the linear address is associated. Linear address will get, so cylinder number into number of surfaces into number of sector per surface plus H into number of sector per surface plus C. Yes will be there. So this will give. So did you study what is M? Number of surfaces. Number of surfaces totally, because this like here is how many 0, 1, 2, 3, 4, 5. Total how many surfaces are there? 6 surfaces. So that completely all surface we are combining, that is a cylinder, right? So number of surface, each surface some tracks will, sectors will be there. So how many sectors per surface? Because everything I am converting into sectors only. Cylinder length also I am converting into sector. Sector number into number of surface into number of sectors per surface, and sector surface number into number of sector per surface and sector number. This we call linear address. What is the linear address, sir? Suppose 0 to 1000 cylinders are there. 1000 cylinders. So like some many more than 10,000 sectors are, we are arranged 0, 1, 2, 3, 4, 5, 7 like 100, 200 like this. That is a linear address. Logical address nothing but suppose 100th sector number is there, 100th sector number, which cylinder number, which surface number it is there. That's what we call logical address. With this respect, please revise this. With respect also they can ask question. So I hope you know this point. I hope you know this point. So now from secondary memory is concerned, there are 3 types of question we can expect. One is size they can ask. Second one time they can ask. Third one cylinder wise they can ask logic. They can give logical address, they will ask linear address. Sometimes they give a linear address, they will ask logical address. This part you need to be observed. So now just move on to the next thing. So next the very important thing is what? Look this all of you. Instruction format, addressing modes and IP. IP is the instruction pipeline. From this chapter. So from this chapter, what are the things need to be studied? What are things need to be revised from this chapter? Instruction format, addressing modes and instruction pipelining. Okay, look this. So you know all of you instruction format, right? Instruction format. So we call machine instruction. We call machine instruction. So this instruction format basically of two. One opcode will be there, opcode will be there, and operand will be there. Operand. But specifically, if I see, we have a mode bit also. Mode bit indicates addressing mode. Mode field nothing but indicates addressing mode. Which addressing mode being used? Getting my point? So this opcode and operand will be there. What is the opcode, sir? Opcode nothing but operation, instruction. Examples here: addition. Getting my point? Addition or subtraction, like a move, like a load. These are the instructions. Operand nothing but data only, right? Data which are involved in the operation to be carried out, right? Which involved in the operation that will carried out in ALU, right? Now see, this instruction format we also called ISA, instruction set architecture also we can say. Please understand. We can call instruction format or ISA, instruction set architecture also we can say. This instruction, see, you know, right, opcodes also classified into many, like data transfer instructions, arithmetic instructions, and program control instruction, like, program control nothing but, jump, branching instructions. Branching instruction consider of program control instructions. Data transfer instruction nothing but load, store, move, push, pop, like this. Arithmetic, like arithmetic instructions, right. So these are the opcode. Now this instruction format also classified, ma'am. So we have a classifications. This instruction format also classified into so many architectures. We have general purpose, general register, CPU organization. Second one, accumulator based architecture. Third one is like a stack based architecture, stack based architecture. Getting my point? So if I take general CPU register nothing but we called 2 or 3 addressing instruction. We also called 2 or 3 addressing instructions. I hope you understand. If I say accumulator nothing but 1 address instruction, we call 1 address instruction. So stack based nothing but 0 address instruction, we call 0 address instructions. So are you able to understand total what will there? 2 address, 3 address, 1 address, 0 address will be there. These are the instruction, addressing instruction we call classified into 3 types of architectures. It is kind of architecture, general register, CPU organization, one type of architecture which support either a 2 or 3 address instruction. If I say accumulator based architectures are having only 1 address instruction. Stack based architectures are 0 address. So what are the differentiations are? You understand. General purpose register, general register type nothing but all general computers. So like if I take Weinmann architecture, we use for general computer design like personal computers or desktop based. These are the personal computers we call, right? Where we use a 2 address or 3 address. Getting even lesser application. Example, if I talk about embedded systems. Embedded system does not have separate operating system. Right? We have microcontroller. We have less number of instruction to compute. Such case the 0 address instruction is preferable. That we call stack based. No separate main memory and cache memory like this. So memory is being used, controller, microcontroller, we have memory. In the memory method stack, by using stack only operation will happen. I hope you studied this all the things. This classification would be there. So based on this question also, what kind of question they can expect are here. So they say, look this all of. In this case question being expected, like suppose instruction, this is instruction format or instruction register is 32-bit is there as in that, please understand. If it is like if I mark it like this, what is there here? Opcode will be there, please understand. Opcode will be there. This operand field will be there. This operand. Operand field, this is given by the addressing mode. Where the address of the operand available given the addressing modes only. Let's take this operand field is 8-bit is there as on that. 8-bit is there, right? Now how many opcodes possible here? How many opcode possible here? Tell me. So for this, how many 8-bit if you remove 24-bit, right? 24 bits are there. Now can I say number of? So number of opcode possible, number of opcodes will be 2 power of 24 or not? Tell me. 2 power of 24 or not? Number of opcode possible 2 power of 24. Whether it is 1 address or 2 address instruction it is. If you have one address field, nothing but one address instruction. This is what? One address instruction. So what is the meaning of one address instruction here? One address instruction, one address is there for one operand. Suppose if I take other thing like this, you understand here. Same 32-bit instruction format if I take, now see 8-bit and 8-bit is there as on that. Opcode 1, opcode like this. This we call two address instruction is what? Two address instruction. Here is a opcode. This operand, sorry operand, this operand. Opcode operand here. So for this how many bits will be there? 16 bit will be there. Now I am writing a number of two address instructions possible equal to 2 power of 16. 2 power of 16. Number of one address instructions possible how many? 2 power of 24. But what question they ask, sir? They can ask sometime, you know. Architecture is supporting one address to both are supporting. And they'll give some, this many one address are there. How many two address possible? They will ask it. Very interesting question, easily solvable. So I'm making like this, you know, example C. So I'm taking this is a 32-bit register, getting my point. So they give an opcode, okay, opcode. Here is a address field, memory field is there. Suppose it is taking 8-bit as on that, 8-bit is taking. Look this. So number of one address instruction possible equal to, this will be 24, right? 24. So 2 power of 24 possible. If they say, please understand, if they say it supports two address instruction also, assume that. What does mean two address means? Please understand. So now understand, look all of you. So this portion need to be divided right like this or not? 8-bit one operand, another 8-bit another operand will be there. Now opcode how many? 16-bit only will be there, right? 16-bit only will be there. Means this portion, some bits are allocated for this address portion or not? This for address portion only. Two address. Here one address. Now suppose if I say only how many two address instruction possible? Nothing but 2 power of 16 I can write. But I am saying that it also support to support the two address instruction. Now how to formulate question they can ask, like, you know, one address or something is there, two address are how many, or two address are given, how many one address is possible, like this. How to understand this question? Suppose example, no, you have 1,000 rupees, only you have 1,000 rupees. So you went for, you know, shopping, like some shop, you have to buy some items. Suppose X type items you already purchased nothing, you collected, you went for billing. So that X type item will cost you 1,000 rupees. The moment you go for billing, you reminded that some other items also you need to buy, but you don't have extra money. What you can do? X type of items already you bought it, going for bill, but you reminded that you need to buy one more other things also you need to buy it, like this. Other things also you want to buy it. Then what to do? You have to drop some quantity of the X type or not. You have to drop some item, then other Y type you have to collect it. Like that, you understand. If it is supported one address instruction, nothing but how many possible? 2 power 24. But it is supporting two address also, nothing but one address will be removed or not. So I'll give the one formula for that. So that will work for anything. Suppose I am taking, like, you know, here in this example 2 power of 24 P I am taking P. P is what? One address instructions. I am taking P is a one address instruction. P how many possible? 2 power 24 is possible. But I am saying that it will also support Q. What is a Q? Q is a two address instruction. It support a Q address. If you want to support Q address, nothing but from 24 bits you have to take 8 bit you have dedicated for this address or not. So that nothing but 2 power 8 instruction will affect from the one address instruction or not. When you want to take the item B type, some of them you have to drop. X item type you have to drop, then only B will take, right? That's what. So this some drop you have to do from one address. How many? 2 power 8 you have to drop it, like 2 power 8 you have to drop it. So this will give the expression. Suppose example, if you want to P you can find, if you want to Q you can find it. What is the P? P is one address instruction. What is the Q? Two address instruction. This way you can formulate. So even you can extend for 3 address instruction also. Even you can extend for 3 address, same way. So for 3 address instruction support nothing but some more 8 will be affected. That r into q power of, so 2 power of 16 you have to write it. So this give the example expression to do it more. So these are the possible question. Other possibility will be, you understand, instruction format he will give. He will say this many instructions supporting, this many fields are the register field, so 2 are there, memory field is there, and immediate field also there. How many, what is the largest integer number you can store? This type of question also they can ask it. So I hope you already studied that part here. Fine. So this is all about instruction format. So next to move on to the addressing modes. Please understand, addressing modes, which is very important theoretical question we can expect from this area. Amlan, is it clear? Are you able to follow? Are you able to follow? So addressing modes, please understand. Addressing modes are, from addressing modes, please understand, very theoretical question we can get it. Theoretical question, some numerical type of question, but easily solvable question in this area. What is the purpose of addressing mode? I'll tell you. Purpose of addressing modes, please understand. So in instruction format we have operand field, right? How the operand field is determined, how the operand reference given in instruction depends on the addressing mode only. Other we understand, addressing mode specify the way operand is represented in instruction field. Means whether it is a memory address or whether it is a register address, is a direct address. So specified by the addressing modes only. Getting my point? Now see, these addressing modes are like you might be studied implied addressing mode. Have you studied implied addressing mode? Second one is immediate addressing mode. Immediate addressing mode. Third one is direct addressing mode. Direct addressing mode. The fourth one is indirect addressing mode. Indirect addressing mode. The fifth one, register addressing mode. Register addressing mode. Sixth one, register indirect addressing mode. Indirect addressing mode. And seventh one, please understand, seventh one is what? PC relative. I'll write here. Seventh one is what? PC relative addressing mode. And eighth one is base register. Base register addressing mode. Ninth one is what? Indexed addressing mode. Indexed addressing mode. 10th one, please understand, this is modified only. Auto increment or decrement addressing mode will be there. So these are the 10 addressing modes are there, ma'am. And understand, implied nothing but stack based architecture, zero address instruction support. Stack based architecture, please understand, stack based architecture having the accumulator implicitly. Please understand. So if I take the one address instruction or zero address instruction, if you take, accumulator will be there, right? By default accumulator will be there. Accumulator based architectures are supporting what? Implied addressing mode. Means if you want to design zero address instruction or one address instructions, accumulator by default should be there. So that is implied addressing mode. Implied nothing but we are not explicitly we are not mentioning the operand. We are not mentioning any explicit operand. Example take, suppose example you take. Look this all of you. Look this all of you. Suppose I am writing negate, I will write it. NEG is an instruction, negate, negation. What is the meaning of negation? Complement. Complement I want to do. Suppose one's complement or two's complement I perform. Sir, where to perform, sir? On which data you are perform negation? So now by default accumulator content. Content in an accumulator that will get negated when you write NEXG. Because we did not specify specially. So that by default it will take. So immediate data nothing but please understand, right? Immediate. Data is part of the instruction only. Operand is part of the instruction. Generally it is useful to access the constant variables, constants. getting constants. Example I'll take it. So add is an instruction, register 1 hash, suppose 50, if I write it. What does mean? So R1 plus 50 results you store in R1. One operand comes from where? Register. Other operand is part of instruction. This is what? Immediate addressing mode. Are you able to understand? This is what? Register addressing mode. Am I right or wrong? Tell me. Am I right or not? So look at this we to understand. Direct addressing mode means data available in memory. So example 1, I'll go with example only. Add register R1 and 50 I am written. This is a direct addressing mode. Direct addressing modes, you understand what is the meaning of this one? At memory location 50 we have a data. That plus you have to add register R1, store in R1 register only. 50 is not a constant, 50 is not a value, it is the address of the memory location. One memory reference required, please understand. We required one memory reference. We required two register references, right? Yes or no? One is for reading, one is for writing. One is for reading, another is for writing. I hope you understand now this direct. What about indirect addressing mode? So indirect addressing mode, please understand. Indirect addressing mode. So let me remove some pages which unused. Look all of you. Look, indirect means what? I am writing example. Add register R1 at the rate suppose 500 I am written. Look this. So this indicates you have to go to first 500. You have to go to 500 in a memory location. You will get one address. With this address you have to go to again that location. Two memory references required. Indirect nothing but, so are you able to understand? Indirect nothing but the instruction has some address. The address to memory location. In this and that memory location we have address. That we call effective address. If you go to effective address you will get a data. Two memory reference required. See, at the rate 500 I written. 500 indicates one address and you go to 500 some more address will be there. So that is giving the memory data value. This what? Register reference here. Memory reference this is. Understood ma? It is understood? So I am trying to say, suppose I is there, suppose I or hash indicate the immediate data. Immediate addressing mode indicates ma, please understand. And this is square bracket is there. Suppose square bracket indicates direct addressing mode. And parenthesis are at the rate symbol, please understand. Parenthesis are at the rate symbol indicate the indirect addressing mode. Getting my point all of you? Suppose any register number is there like this. This indicates the register addressing mode. This is the symbols you can observe it. This may be useful to you. As symbol is there, indicate what? Immediate data. And direct nothing but some direct value will be there. Some value are this one. Indicate that direct addressing mode. Example, if you see this example, if you see here. Value is there. Indicate what? Memory direct. Parenthesis there are at the rate symbol is that indicate indirect data. So I hope you understand this example. Look at this now. So register direct means nothing but what? Register direct meaning register number is there. So let us look into register indirect. Suppose example 1, right? This example 2 I am taking. Add register R1. So register R2 like this is there ma. Now if I ask question, what are the addressing modes are involved here? What are the addressing modes are involved? By looking this one you can say register addressing mode. This is a register addressing mode. Now parenthesis indication what? Indirect, right? So what does mean you? So if you take the content of register, go to memory like this memory, you will get a data. Means this involve one register reference, one memory reference. One memory reference. I hope you understand this point. Yes, Amlan, is it clear? Because this type of question they frame, now you are able to understand what address mode they used. And sometimes they ask how many memory references required for this instruction also they can ask. If I want to compute this instruction, how many memory reference required? How many memory reference are required? They can ask it. So this is the register indirect, ma'am. So I will study addressing mode. You might see the symbolic representation. I don't want to take the diagram part actually. So if I take the diagram part, you may get it. But I am hoping you know already diagram part. That's what directly I am taking here. So content of the register having the memory address. Register ought to have the address. Content, the content of the address of the memory location. You go to memory, you will get a data. That's what register indirect. Register indirect. Getting my point, all of you. So look at another point. Look at another point. Look at another point. Suppose add is there. Add. Please understand. Add register R1. So 20 of R2 is given. Suppose 20 of R2 given. What is this addressing mode? This is what? Register addressing mode only. What about this here? Please understand. So content, this R2 is the memory location. For this you have to compute add the 10. So this gives the effective address. Okay. Now you understand here. You have to understand here. Please look this one. Base register or index register will be there here. Base register, index register will be there. Look at this. PC relative addressing is specially used for branch type, handling with the branch type instructions. I hope you're getting my point. Have you studied PC relative addressing mode? Branch type instruction, nothing but what is the branch type instruction? I fetched one instruction, fetched an instruction, branch instruction, conditional branch is there, I am checking the condition is true, it will jump for target address or not. So such a case, current value of the PC I am adding to some offset value, it will give the target address. To deal with all branch type instruction, we use what? PC relative addressing mode. PC relative addressing mode. Now see. So if I write this instruction, I am adding this 10 to the content of R2. This R2 value may contain the base. Please understand, base. For that base, I am adding offset to get the effective address. This indicates the base register addressing mode. Or sometime understand, in the question if we say, if you question R2 has some index value, for that offset I am adding, so base value I am adding, that may come to the index register also, based on the question. So this can be, please, this can be base register, this can be index register also, based on the context in the question, because same only. In case of base register, in case of index register, what I will do? Base value I am adding to the index, right? Yes or no? Or offset value we are added to the base value, base address. Both are same only. Application will vary. Index register generally we use for accessing the array elements. Base register we are. So type in this case what? Here they won't ask any question. What type of question? Nothing but they say, they can say the second operand is 10 of R2 is there. They can ask which addressing mode it is used. Whenever some value you are adding to some register, if you are performing any computation, that can be a base address register, that can be index address register. This is one type of question they can ask. Other type of question they can ask here. During this execution of this instruction, I used an index register or base address register. How many memory operations required for computing this one? Tell me. If I want to compute this instruction, how many memory operations required? How many memory operations required? Can you tell me? See, now first of all, 10 plus 10 I have to add to R2 content. Then I have to visit memory. So that means one register reference required, one memory reference required. Getting my point? So here is one register reference required, right? One register reference. Then after adding, you have to store in where in R1 only, right? One more register reference required. Total 2 register references required. Here 2 or 3 required, and 1 memory reference required. I am not worrying of the fetching of instruction. During execution time I am asking. If fetching also consider fetch, you have to fetch the instruction from memory also. That is also one memory operation. Suppose one more question I will ask. Add register R1. Tell me now how many memory references required during execution cycle only. So like no, we have a fetch cycle, decode cycle, execute and store cycle is there. During execution cycle only, how many memory reference required to perform this operation? This is the first question. Second question, what are the addressing modes are used here? So first question, memory reference, please understand, it is a indirect, right? Yes or no? Indirect only? Register indirect or not? One register reference required, one memory reference required as a source operand. For a destination, when you compute, you have to store in memory also, right? So one more time register reference required, one more time memory reference required. For this, one register reference required. First time I am fetching, right? Fetching. It is a source operand. It is a source plus destination. One more memory reference required. Total how many required? Memory 1, 2, 3. 3 required during execution cycle. 3. If total entire cycle, if you take it, addition, fetching also required, right? That is also required, one more. So total 4 I can say. During execution time, 3 cycles required, 3 memory operations required here. Now what addressing mode? Indirect addressing mode it is. Register indirect addressing mode. Here it could be base or it could be index based on the option. It could be base addressing mode or it could be index addressing mode. This is another type of question you can see. This is what? Another type of question. Understood? Understood all of you? Amlan? Respond? Yes. So possibility I am telling, there was a question also actually. This same question, this was a question in 2000 some, I could not remember, 14 paper or 15 paper, the same question is asked. Same exactly, add this, instead of R1 something you mentioned, same format only. They asked how many number of memory operation required during execution cycle, like the execution cycle here. So total instruction cycle if I take, have to fetch instruction also, right? Have to fetch instruction also from memory. That is one extra. But he asked me during execution cycle. I have to fetch the source operand, I have to fetch this destination source operand, I have to perform addition, you have to store back to memory. So I required 3 cycles required. Got it, all of you? Got it? Chalo, we'll move to next topic. Some pages I want to delete. So we understand what are things need to be studied from instruction format and addressing modes. So next one will move on to the instruction pipeline. Instruction pipeline. Yes. Here is the first thing you have to understand here. Under instruction pipeline, clock per instruction average will be 1. This is what we have proven. And theoretically you might be studied. We can prove it. average clock per instruction will be 1 in instruction. And second thing, you must know that speed up factor, how to get the speed up factor, how to find out the speed up factor if I take S equal to time with non-pipeline by time with non-pipeline by time with pipeline. Am I right or wrong? Speed of factor S equal to given like time with non-pipeline pipeline. This way we can find out the speed of factor S. And third one, they can also ask the efficiency of the pipeline that we can measure. That we measure. S is a speed of factor out of K. K is a, what is a K? K is a number of stages. So number of stages in the instruction pipeline. This is the three things you have to understand here. Clock per instruction average clock per instruction pipeline will be 1. So how to get the speed up factor, how to get the efficiency, we understand. So fourth point you have to observe here, this clock per instruction average, I said 1, right? 1 I said 1. So this is giving a good performance, I can say. It is an ideal performance. When the system is performing ideally, you will get clock per instruction 1. That means understand speed of factor you achieve to K. How much speed of factor you can get it? K. So efficiency will be 100%. No, here S is less than or equal to K, right? S is less than or equal to K. I can say S is greater than 1, comma, S must be less than or equal to K here. Speed of factor, maximum you can get K. What case speed of factor you can get K? Ideal case. Ideal case nothing but there is no any delay in the pipeline. So if you are getting S equal to K, nothing but efficiency will be 1. Efficiency will nothing but 100% utilization. Ideal case you will get a clock per instruction 1. But what happens, please understand, look all of you. There are two things will affect the performance of the instruction pipeline. There are two things will affect the performance of the instruction pipeline. One is uneven stage delays. Uneven stage delays. Uneven stage delay nothing but what? Stage delays are different. So I assumed how we got clock per instruction 1. All the stages are taking same time. Then we will get uneven stage delays practical possible, that will impact on the performance. Second one, dependency among the instructions also will impact on the speed of factor. So now see, if the uneven stage delay or dependency is there, clock per instruction will increase more than 1 or not? Tell me, do you agree? When uneven stage delays are there and if there is a dependency among the instruction, average clock per instruction will increase more than 1 or not? Tell me. Yes or no? Yes or no? Yes or no? So that 1 plus I am taking as a delta. What is delta, sir? Delta is nothing but how much such frequency of the dependency is there. Means percentage of the frequency, means frequency meaning what? What is frequency here? How much such rate of dependency multiplied by how many stalls happen for each dependency. Stalls, number of stalls, the delta. Such case it will increase more than 1. Mean example, so 20% instruction are dependent. So each dependent instruction taking extra 2 cycles required, that stalls. So 20% into 2, 20% 0.4. So 1 plus 0.4 will be what? 1.4 will be the average clock per instruction will come. So this point you have to observe it. So another point, all of you. Another point you know. So cycle time of the pipeline, TP, cycle time of pipeline will be how to get maximum of stage delays, right? Stage delay. Suppose ith stage delay maximum is there, plus some buffer overhead you have to take it. Yes or no? This you know, right, all of you. Whenever instruction pipeline stages are different delay is there, how to take the cycle time of the pipeline? Nothing but maximum stage delay you have to remember. In case of pipeline, TP is the cycle time of, I am writing cycle time of pipeline. This is another important thing you have to notice. So if you know the cycle time, then you can get this time with pipeline, non-pipeline, you can get the speed of factor, you can get the efficiency also. Fine. So I hope this understand. All of you got the point? This one 1 plus delta. When there is a dependency, it will increase the clock per instruction. So look at the question. They asked, 5-stage instruction pipeline is used to implement the two programs A and B. Program A has 10 instructions and program B has 400 instructions. The pipeline is operated with 4 megahertz clock. How much time is consumed program A and program B? So suppose program A I am taking, time for program A. So pipeline, how many 5-stage pipeline, right? See, we know. So time how to get K plus N minus 1 into this TP, cycle time TP, right? Yes or no? What is the K? 5 stages. How many instructions are there? Program A, 10 instruction. 10 minus 1, 9. So into TP, cycle time we don't know. 14 into TP. So how to get that for TP cycle time? Generally stage delay they'll give, but in this case stage delay not given. But they said this is operated with what? 4 megahertz. Clock rate given. Do you know? Clock rate can be converted into time. 1 by clock rate is a time. Do you agree, all of you? 1 by clock rate is a time. So what I can 1 by clock rate? 4 megahertz. So this we can write 14 into, so 1 by 4. Mega means what? 10 power 6 hertz. Send upside 10 power minus 6. So can I write 1 by 4 into mega, nothing but I can convert into microseconds. Then that value will be, how much will be? So 7 by 2, right? 7 by 2 means 7 by 2 only, right? 2 2s are 2, 7 are 7 by 2, 3.5. So 3.5 microseconds you will get. Similarly, program B. Program B. What is program B? K plus K stage, how many? 5 plus, how many instructions are there? 400. So 399 into, this is how much? 1 by 4 minutes. So 0.25. Am I right or not? So 1 by 4 microseconds. This will be 4 naught. 4 divided by 4 microseconds. This give 101 microseconds. Am I right or wrong? Yes or no? Yes, yes, yes. 1 by frequency equal to T. That's what 1 by 4 megahertz I written. Mega means we can have 10 power 6. Send upside. 10 power minus 6, 1 microsecond. 1 by 4 microsecond. So is it correct? So this way you can calculate it. This way you can calculate it. Chalo, we'll move on to other things. So I want to look at this question, all of you. Look at this question. Consider a 4-stage pipeline processor. Number of cycles needed by the 4 instruction I1, I2, I3, I4 in stages S1, S2 are shown below. What is the number of cycles needed to execute the above program? They are asking. Program has 4 instructions. How many clock cycles required to do it? Then how to do? You have to draw the Gantt. You have to draw the what timing diagram, right? Yes. Do you know Amlan? Do you know how to draw the timing diagram for this? Say yes or no? Yes or no? So you know, right? Stage 1 instruction, stage 1 taking 2 clocks, stage 1 taking 3 clocks, stage 1 taking 2 clocks. Like that, you can draw the timing diagram. You will get the number of clock cycles. Can you do it this one? Yes. But why I have taken, you know already. But why I have taken? Because drawing the timing diagram will be take more time for this special question. It will take more time. Yes or no? Yes or no? Then sir, by looking the table, how can I get it? If the question is framed like this, simple to answer it, ma. What you can do, I'll tell you. Whenever the question is given, what you can do, simply, you know, first row and column update it. 2 plus 1, how much, ma? 3. So 3 plus 3, how much? 6. 6 plus 1, how much? 7. 7. Now here 2 plus 3, how much? 2 plus 3, 5. 5 plus 2, how much? 7. 7 plus 1, how much? 8 here. Now these are the cells we need to update. How to update, sir? So simply maximum of these two, what is the value? Maximum of these two, what is the value? 5. 5 plus 1, 6. Like this one, right? So maximum of these two, What is the maximum of this 2? 6. 6 plus 2 almost 8. What is the maximum of this 2? 8. 8 plus 2 almost 10. So now what is the maximum of this 2? What is the maximum of this 2? 7. 7 plus 1, 8. What is the maximum of this 2? 8. 8 plus 2, 10. What is the maximum of this 2? What is the maximum of this 2? 10. 10 plus 3, 13. So what is the maximum of this 2? 8. 8 plus 1, 9. What is the maximum of this 2? 10. 10 plus 1, 11. What is the maximum of this 2? 13. 13 plus 1, 14. If you draw, you will get 14 only. You get 14 only. I am just damn sure I am saying that. If you draw the timing diagram for this, you will get the number of clock cycles to complete this 4 instruction under 4, so you will get 14 only. And it is not only works for this problem, it is also works for, operand forwarding. You studied, right? Operand forwarding. Data dependency problem is operand forwarding is there, right? That also it will help you for us. Sir, how you understand, sir? Simply no. First you draw the diagram, timing diagram. If you see what I will say here, instruction 1 is there, ma'am. Instruction 1, after 2 clock stage 1 will work. After 5 clock stage 2 come work over. After 7 clock, after 7 clock stage 3 work will over. After 8th clock stage 4 work will over, right? That's what I added. When you look at the second instruction can be used the stage 1 work after completion only, right? Yes or no? See, I2 I can use the S1 stage after this only. After 2 only you can use 2 plus 1, 3 complete. I3 can be used S1 after 2 plus 1 only. That's what 3 plus 3 I written 6. Instruction 4 can use the stage 1 work after 2 plus 1, 1 plus 3, like after this 6 only you can use 7 I written. That's what row and column updated. But why I taken maximum, sir? Reason I am telling you. I2 instruction is there if you want to use the stage 2 work. Any instruction if you want to use the stage 2, the stage 2 should complete the previous work, right? The stage 2 should complete the previous instruction work. Yes or no? Previous instruction work should complete. One more thing. If you want to use the stage 2, previous instruction work you have to complete it, right? Yes or no? Now your instruction should complete the previous stage work. Suppose example I2 is there, I2 instruction I want to go to S2. I2 should complete the S1 work and S2 should free from the I1 work. That is the reason I am taking maximum. See, I2 instruction I want to give the stage 2 here, I want to give it. When stage 2 free? After 5 clock only. I2 saying that I am free after 3 only, but I cannot give immediately. I cannot add it 3 plus 1, 4. I2, suppose when you counting like row 3 plus 1, 4, 4 plus 1, 5, 5 plus 1, 6, I cannot do it because I2 instruction, S1 work over at 3 only. It is free. But stage 2 is not free. It is busy with the previous stage work, right? Previous instruction. That's what I am waiting for this one, 5. And that's what I am taking 5, maximum of this 2. 5 plus 1, 6. Getting my point? Example here is there. I want to give the I4 instruction to stage 2 work, stage 2. Is I4 saying that my stage 1 work or 7 only. But I cannot add it here because the stage 2 is busy with I3 instruction. It is completing it at 8. Maximum you have to wait 8. Maximum. So 8. After 8 only I am adding 2. I hope you understand now. Yes. Now you will enjoy the other things. So simply you can update the row, update the column, adding the value. When you updating this one, you just add it. Take the maximum, add maximum, you will get answer. Within a time you can solve it because timing diagram takes and people can also confuse because adding this cells and stalls will be there, right? Chalo. Other thing. As I mentioned here, pipeline performance affected by the dependence among the instruction. Please understand. So dependency among the instruction, right? There are 3 types of dependency will be there. Yes or no, all of you? One is data dependency, Yes or no? Second is a control dependency. Control dependency. Third one is structural dependency. Structural dependency. I hope you studied. Data depends nothing but arithmetic operation will create a problem. Arithmetic operations will result in data dependency. Now branch instructions. Branch type instruction causes the control dependency. Structural nothing but limited resource. Limited resources cause the structural dependency. So do you know what are the solution for data dependency? What are the solution for data dependency? Do you know all of you? What is the solution for data dependency? First one is stalls. Introduction of the stalls, you can place it. Second one, placing the independent instruction between the dependent one. Third one is operand forwarding. I hope you understand. Operand forwarding. Am I right or not? Solution to the data dependency are introduction of the stalls or independent instruction placing the between dependent one or operand forwarding. Now what are the solution for control dependency? Multiple pipelines, early detection, delay, one delay slot, and prediction methods are there. Yes or no? Prediction method, one delay slot, multiple pipelines are the solution for control dependency. Structural dependency is nothing but duplication of the resource. When the resource is not available, that's a problem occur, right? Duplicate the resource. So that will come. So let us just focus on this one, operand forwarding. Operand forwarding. One question I'll take it. Look, this question. This question was asked in 2015 paper. Lengthy question actually. But nicely we can solve it. Easily we can solve it. Look this. Consider the sequence of machine instruction given below. Instruction 1, instruction 2, instruction 3, instruction 4. Total. In the above sequence, R0 to R8 are general purpose registers. In the instruction shown, the first register stores the result of the operation performed on the second and third register. The sequence of instructions to be executed in the pipeline processor with the following 4 stages are there. Instruction fetch, instruction decode, operand fetch, execute and write back. 4 stage instruction pipeline they used. Look. Instruction fetch, operand fetch, write back stage takes how many clock cycles? 1 clock cycle each for any instruction. The perform stage takes, execution takes a 1 clock cycle for addition, subtraction, 3 clocks for multiplication, 5 clocks for division. The pipeline processor uses operand forwarding from perform to operand fetch stage. Number of clock cycles taken for the execute of the above sequence of instruction dash. So do you know there is a dependency is there? You can see, go and see. Dependency is there. See, what is the dependency? R1, R0, R1 is storing R5. R2, R3 is storing R6, right? Fine. This both are independent only. But you see R5, R6 are there, which are, this instruction depends on both or not? Tell me. Yes or no? Yes or no, all of you? Yes or no, all of you? This depends on this or not? Tell me. So now instructions are dependents are there. To resolve the dependency, what mechanism they used? Operand forwarding. Do you know mechanism operand forwarding, how it will work? Amlan, please stay connected because interesting thing you will going to get it now. Yes. Did you study operand forwarding mechanism? What we do, before storing the results, we are forwarding to next stage, right? Yes or no? So after execution, we store into write back, right? Before write backing, I am transferring into next stage so that I can minimize it. That is what operand forwarding. Suppose if you use operand forward mechanism, dependency problem resolved or not? Resolved? Resolving. Fine. So to answer this question, you have to draw the timing diagram actually. Yes or no? Instruction 1, you fetch, decode, execute, write back, forward. You have to do. Then you can count the number of clock cycles. I am saying that use the tabular method to solve this problem. Why I am suggesting to use a tabular method? Because they use the operand forwarding. If I use operand forwarding, problem is solved. It is normal execution only, no dependency, independent instruction execution. Let's take, suppose if I take stage, like what is the stages are there? Fetch is there, right? Fetch, decode, operand fetch is there, perform operation and write back is there, right? Yes. What are the instructions are there, ma? Go and see quickly. Multiplication, division, addition, subtraction, right? 4 instructions are there. Multiplication, division, subtraction, addition. So, am I right or wrong? Division, addition, subtraction, fine. So I'm plotting what are the instruction, how many clocks required on the stages. They said fetch, decode, write back. So what they said? Fetch, instruction fetch, operand fetch, write back. 3 stages take 1 clock cycle only. 1, 2, 3, 4. 4 stages only, ma. Sorry, I missed it. So this is the write back, right? Write back. So go and see. Pipeline 4, instruction fetch, decode, acha, 1 only. Operand fetch is there. Okay. This is itself instruction decode also. This is operand fetch is there. This is perform operation is there. Fine. So this will take all 1 clock cycle only, right? Fetch, operand fetch, write back, all will take 1 clock cycle only. Is it same things I mentioned? And perform operation, 1 clock cycle for addition subtraction, 3 clocks for multiplication. Addition subtraction 1 clock only, 3 clocks for multiplication, 5 clocks for a division. This only given, right? So just plot it immediately table by reading the data, because operative forwarding, if you use it, what does mean? This is, it is solving the problem. Add it, 1 plus 1 how much? This is 2, this is 3, this is 4, right? Then 1 plus 1, 2, 2 plus 3, 5, this is 6. Maximum of this 2, 2, this is 3. Maximum of this 2, 3, 3 plus 1, 4. Maximum of this 2, 4, 4 plus 1, 5. Maximum of this 2, 5, 5 plus 5, 10. Maximum of this 2, 10, 10 plus 1, 11. Maximum of this 2, 11, 11 plus 1, 12. Now, maximum of this 2, 10. So 10 plus 1, 11. Maximum of this 2, 11 only, 11 plus 1, 12. Maximum of this 12, 12 plus 1, 13. You will get 13. If you draw Gantt chart also, you will get same. Sorry, if you draw the timing diagram also, you will get it same. This is a previous year question, ma'am. This is a previous year question. Go and verify that. You have answer of 13 clocks. But reading and drawing the timing diagram takes time. So this will give the right direct answer. Sir, how I able to know that? That's what I am giving a clue. If the question is framed from operand forwarding, then you just count the how many instructions, how many stages, what are the clocks are taking each stage, just plot it in a table, get the value, you will get the answer. This is damn sure giving. But what is the thing is there? Dependency instructions are there and operand forwarding is there. If other than this given, this may not work also. For especially for operand forwarding, I am telling you. Fine, ma. I hope you understand now. Now, control dependency I mentioned, multiple pipelines are prediction methods. You can use it, so you can use it, so revise, because control dependency also important topics. We can expect the question from that. Fine. So I took here also, you can solve it. Pipelines support the overlapping of instruction except the conditional branch instruction. The third stage of the 5-stage instruction pipeline is capable of evaluating condition and providing the target address of the conditional branch instruction. The pipeline will not fetch the target of the conditional branch instruction until the branch outcome is known. The pipeline is operated 1 GHz clock. 20% of 10 power 6 instructions are conditional branch. How much time is required to implement the above program is dash. First you get the, what I am trying to say, get the clock per instruction. Clock per instruction. As I said, generally clock per instruction average will take only 1. But there are branch instructions are there. What is said branch? 20% of 10 power 6 branch instructions are there. 20% of 10 power instructions are there. Am I right or not? Now say what I am trying to do, 20% are there. 20% branch instructions. Yes. Yes or no? And each branch instruction will result in how many stalls? They said third stage is the generated of the 5-stage instruction pipeline. You know, third stage is generating the target address. 3 minus 1, 3 minus 1, 2 stalls will be there. 2 stalls will be there, like this, you understand. So 1 plus 0.4, it is a 1.4. Now time for a program, right? 10 power of instructions are there into 1.4. Clock period given. What a clock period given? 1 gigahertz. Nothing but if you convert 1 nanosecond, you will get it. 1 nanosecond. You can multiply, right? This will give 10 power of 6. So 1 nanosecond equal to, can we write? So 10 power of 6 into 1.4 into, can we write 10 power of minus 6 milliseconds? Can we write? Nanosecond equal to 10 power of minus 6 milliseconds. That gives 1.4 milliseconds is the answer. First you get the one instruction time, multiply it to all the instructions. That's only we can do it. This only clue. What is the clue? Naturally clock per instruction 1. Due to dependency, extra will take. How much extra? 20% are there. 20% are conditional branch, which will result in what? 2 will happen, right? Because they said third stage is the instruction generator, address generator. So whenever third stage mention 3 minus 1, you do it. Fourth stage mention 4 minus 1. K stage mention K minus 1 will be the stalls. That you have to generalize it. I hope you understand, ma. I hope you understand. In the IO organization, so major important topic you go and refer it, you know, data transfer methods. So one is programmed IO, second one is interrupt driven IO, third one is DMA. This is important. DMA is important. DMA part you need to revise. What I am trying to show DMA, very simple. DMA, like no, DMA means you understand, it is a DMA controller. It is used to transfer the bulk amount of data. From disk to memory without involvement of the processor. During DMA transfer, CPU will be blocked only. CPU will not involve. That's one important point you have to understand. Other models, if you see programmed IO case, CPU will involve. Every instruction cycle, it will check the status of the device, whether it is ready or not. If it is ready, it will transfer the data. Each and every instruction cycle, processor will check the status of the device. Under interrupt driven IO, every instruction cycle it won't check, means checking nothing but device can be interrupted. Whenever a device is ready, it can interrupt running process. So now running process will check the, after every instruction cycle, interrupt value vector will check, is there an interrupt or not. If the interrupt is there, it will perform, otherwise won't perform. But in a DMA case, there won't be any concept. DMA itself put a request for system bus, I required system bus to transfer the data. Now CPU will release the system bus, so it will initiate the IO operation. Who is initiate? DMA will initiate. Please understand, in order to implement the multi-programmed operating system, hardware's point of view, DMA support is highly needed. That's what OS point of view also you will come to know DMA part. But implementation, working principles, all you study from CO point of view only. So this part you focus. That's it. The major things we covered. So I am suggesting you, all of you, once again. So from tomorrow, if you count it, we have hardly 10 days time. Exactly 10 days time is there. In this 10 days time, try to revise many times more. Because you have to understand the concepts. Some concepts we maybe forget also, right, during our preparation. So just schedule the time according to your subjects, how many subjects need to be revised. So revise it, understand the topics, and little bit do the practice. But don't solve this moment as PYQs. Because if you start practicing PYQs, if you are unable to solve it any question, then unnecessarily you will demotivate. And also, if you attempt the mock test, if you are getting less marks, example, suppose you are getting only 30-40 marks, so do not demotivate at all, because these mock tests will not come, right? Exam is different. There are plenty of examples I have seen. Those who are not able to perform well in mock test, they perform well in GATE exam, because that 3 hours is a matter. So we have to very, very pleasant. This next to 10 days, you should be very calm and pleasant. So try to eat the food, proper food, and you must have proper sleep also. Do little meditation, little exercises. Avoid all social media things. Better keep mobile outside. Don't use the mobile. For any necessary things only use it. Yourself, make it calm the next 10 days. So that what happens, if you are in calm and cool, then the GATE exam is aptitude exam, right? Aptitude. There are high chances are there, some questions, some areas you may not study it, by reading that question you are able to answer it. That is possible. Other thing I am telling you, if you are taking the pressure as a GATE exam as a pressure, known question also unable to solve it. Are you getting my, you know already all the things, but you are not able to solve it because of that exam pressure. If you are in a cool mind, some areas if not at all covered, but you are able to solve, because aptitude, basically GATE exam is all about aptitude in the concepts. All the various subjects if you take, they are playing aptitude on concepts only, so that you can do it. So from the CO is concerned, try to focus pipeline area, cache address mapping, memory hierarchy. If you take number system, floating point areas, in IO part, take more focus on DMA part. So these are there, try to revise as much as possible, and little practice, 1 or 2 questions each, you can practice it. Once again, I'm 27th, I'm coming on a live for quick revision on operating system. Kindly present and inform to your friends also, so that they can also join on 27th. There also I will do the revision on entire operating system. Same way I will take all the topics, what are the important things, each topic will observe it. Fine. So I hope you understand the session. I hope you benefited from this session, ma'am. Thank you so much for connecting this.